we'll cover another fascinating topic, cache coherence. How many of you have seen cache coherence before? Some people have taken computer architecture. Have you seen it in computer architecture course? Yes? Who's seen it in a different course? Which one? Oh, yeah, that's right. I know. Which is closely related.
Yeah.
How about a different course? Distributed systems? No? Not yet, yeah. Okay, and we're going to get the computer architecture perspective, but you can, of course, imagine cache coherence is a bigger topic, right? If you have a cache, any type of cache, you can keep it coherent across a system. Although usually, if you build a very large-scale distributed systems, you don't do that. You use message passing, which by definition doesn't have global shared memory, as you learned yesterday, if you didn't know before. Then you don't have this cache coherence problem because you don't have the same address cached in two different locations in the system, right? Okay, so this is essentially a slide kind of based on from yesterday, the next two slides, so it's going to be a reminder. Essentially, we were talking about caching in multiprocessors, and caching complicates multiple things, right? We talked about memory ordering yesterday, memory consistency, and we talked about caching complicating the ordering of all operations. Basically, a memory location can be present in multiple caches, and this prevents the effect of a store or load to be seen by other processors. If a processor has cached a location, it does loads or stores to it, and other processors don't see this operation. This means that the global order of all memory operations is different across different processors, and we know that that's a problem from yesterday. Right? So if you have caching, then you need to ensure that there's some good global order for memory ordering, memory consistency reasons, so that you can actually get your programs correct. But that's not the only problem that you get with caching. It also complicates the ordering of operations on a single memory location. This is, remember, memory consistency was about the ordering of all operations. This was a global order. Whereas if we're, in this one, we're concerned about the ordering of operations on a single memory location, single address. And again, this is because a single memory location can be present in multiple caches. And this makes it difficult for the processors that have cached the same memory location to have the correct value of that location, especially if some other processor updates it. Right? If some other processor updates that location, you have no idea that other processor has updated it if you don't do something special about it, right? And that something special is really the idea of coherence, providing coherence in the caches such that whenever one processor updates a location, the other processor doesn't get the wrong value. Let me put it that way. You don't have to get that value immediately, but you should not get the wrong value. Okay, so this is, I will emphasize this again, you saw the slide yesterday, but these are two completely different concepts. It's amazing that people confuse these concepts, even in academia. Whenever you submit a paper, you get really weird reviews. You talk about coherence and they misunderstand you completely. Maybe sometimes it's because you don't write it very well, perhaps that's also true, but people confuse it, so don't confuse it after taking this class. Essentially, consistency is about ordering of all memory operations from different processors to different memory locations. It's a global ordering of all access to all memory locations. Now, yesterday we talked about sequential consistency, and then we talked about more relaxed consistency models. On the other hand, coherence is completely different. It's about the ordering of operations from different processors to the same memory location. And this is essentially local ordering of accesses to each cache block. Again, it doesn't have to be cache block. It can be any granularity, actually. It can be the granularity of update in the end. But in modern systems, this is enforced at the cache block granularity because it's a convenient granularity. But we will see that it doesn't have to be that way. It could be a coarser granularity. It could be also a finer granularity. When coherence was first proposed, actually, it was word granularity when you update things. Okay, so that's what we're going to talk about. These are some readings. I say required, but I mean, there's no required reading, as you know. It's required for your understanding. And I like this Color and Sing book in terms of its treatment on coherence. It's an old book on parallel computer architecture, so if you have it, you should read it. And as I mentioned, we're going to talk a lot about this protocol, MSI Protocol, which is also called the Illinois Protocol, that was published in this conference. It's a beautiful paper, actually. I'd recommend reading it, even though we don't have time to assign it, I think, in the remaining time frame we have in the course. And there are a bunch of other papers that are interesting over here. This is actually the first paper that proposed directory-based cache coherence, which we will also talk about. But it's a bit harder to read. Okay. So basically, we're really talking about the global shared memory model. As you know, in this model, programs communicate through shared memory processors communicate through shared memory. And whenever processor 0 writes to an address, processor 1 reads, and this clearly implies communication between the two. As I mentioned yesterday, this is not explicit, right? This is implicit. In message passing, it's completely explicit. You send a message to this processor, and that's done explicitly. That's why you don't have a coherence problem, because you don't even share the address space, right? Or you explicitly specify the coherence if you have some mixed model. Here, it's completely implicit. You write to a memory location, and somebody else reads from that memory location. And clearly, each read should receive the last value written by anyone, right? Otherwise, you will have a problem with what this processor has written to this memory location and what this processor read. And this requires synchronization. This means that what does last written mean, right? What is this memory location cached is cached at the either end. It could be cached in both of those places, right? So this is the pictorial view. Basically, if multiple processors cache the same block, how do they ensure they all see a consistent state? Unfortunately, there's no better word than consistent over here, so you can see the overloading. And it should really be coherent state, but for some reason, consistent is a better word over here, I think, in English. But never confuse what is called memory consistency with memory coherence. Okay, basically, we're talking about this location X. It has some value, and one processor loads it, caches it. It has that value now, and their processor does a load, caches it. Now, this other processor, processor 1, writes to that value, updates it. It becomes 2000. Now the question is, when this processor loads the same location, what value should it get? It should not load 1000, basically, because it's already updated over here, right? Okay, so whose responsibility is it to satisfy this, right? Clearly, if we define the problem this way, then whenever you have multiple cached copies in of a location in the system, everybody should see the latest update, right? Whenever they need it, of course, right? If they don't read it, then they don't need to care about that location. That's the difference, again, between memory consistency and coherence. You have to read that location to really care about it, right? Because it's about a single memory location. Okay, so then the question is whose responsibilities? So we're going to talk about a lot of software, but we're going to dismiss a lot of it. Even though it's big in the slide, this is going to be what we're going to focus on. Okay, let's talk about software a bit. The basic question over here is, can the programmer somehow ensure coherence if caches are invisible to software? Invisible is a very strong word. This is very difficult, I think. I guess they could assume that the location is somehow cached, and with every shared data update, they could do something. So it's possible to do it, but with a lot of overhead. Right? One example high overhead mechanism is page-level coherence, right? So basically, whenever you're writing to a location, you somehow lock the page. And of course, locking the page is something that's very important, right? What does that mean? You need to write to a memory location to lock a page, probably, unless you have a special mechanism, meaning that you need to provide coherence on that lock, because somebody else may be locking the same page. So you cannot just provide page-level coherence by itself. You need to provide some coherence for the locking mechanism to ensure that you're the only one who's accessing the page or who's writing to the page. So think about this a little bit. It's possible in today's systems that you say, this page I've locked and nobody else can write to it. And whenever someone else writes to it, there's an exception and something happens in the system. And that's how you handle coherence, right? It's possible to do it, but it's not a great way of doing it. And that requires the locking mechanism to be coherent also, because if you do that through shared memory again, somebody else can try to lock that page also. And then how do you provide coherence to that lock? So one way of providing coherence to that lock is basically making that non-cacheable. Right? Basically, you explicitly say, this particular location, it's going to be non-cacheable. Nobody can cache it. Then you don't need to provide coherence on that location, right? Then you can actually handle this locking of a coarser-grained mechanism easily, because everybody has to go to memory to update that location, which means that there's only a single copy. And if there's a single copy, there's no coherence problem. Does that make sense? I'm going through these relatively quickly because these are well-known mechanisms, but they have very, very high overhead. If you program with this sort of mechanism. And if you're doing a lot of updates to shared data, you'll get a lot of overhead in your program. It's really a waste of time in the end. Okay, so clearly a combination of this non-cacheable and coarse-grained coherence is doable. It can be done in systems. If you're not really, if you don't have another option, maybe you should do it. But this is very coarse-grained, basically. Whenever you update a page, you basically lock the page, and if somebody else wants to update that page, they need to somehow get the lock to that page, meaning that this is all done through the page tables. This other processor doesn't have access to that page table, so it's really about page protection, right? You know about virtual memory. Whenever you actually say, "Oh, I'm the only one who was accessing the page," this means that other people should not be able to access the page. Whenever they access that page to write to it, they should get a write protection fault. If they get a write protection fault, you achieve coherence because you have the permission to write to that page and nobody else. And when you get a write protection fault, then you handle it in software. Right? Then you can say, okay, now you're the one who can write to it, and this other processor who had the write permission doesn't have write permission anymore, and you give the write permission to the processor who wants to write to it. So you can keep doing this through the page table entries, which is a huge mess. So you don't want to do that, I think, overall. So you can go finer-grained. But there's a problem with going finer-grained. So how do you go fine-grained, right? Clearly, we don't have fine-grained protection mechanisms in existing systems, which is a very interesting area to look into. If you had a very fine-grained protection, memory protection, potentially that could be used for coherence. But of course, very fine-grained protection mechanisms is a research area still. How do you actually provide protection at a byte granularity, for example? Can you protect this byte such that only this process can access it, and no other process? Clearly, virtual memory doesn't provide support for that today. But going forward, people are researching that area. Assume that doesn't exist. Maybe there are other options, right? Maybe you actually add new instructions into the instruction set architecture such that the programmer can, now the programmer knows about the caches. You can clearly see that. The programmer can invalidate or get rid of the block if somebody else is going to write to it. None of these are really great, actually, but let's take a look. So flush local A, for example, flushes or invalidates a cache block containing some address A from a processor's local cache. So this local cache flushes that block. Flush global means essentially whenever you execute this instruction, there's a message that's sent to all processor's caches, and all of this processor's caches evict that block, get rid of that block. This sounds more interesting, perhaps, right? Whenever you're writing to a cache block, maybe you issue a flush global beforehand, and then you write to it. Now, this sounds nice, but it's not a good solution, because what happens if someone else does another flush global in between, right? Then basically it doesn't work. You really need to provide atomicity between the flush global and the instruction that comes after, that writes to that location. Because if somebody sneaks in another flush global, or if somebody sneaks in another read to that location after you issued a flush global, then basically you really don't have the only cache copy to write to at that point in time. So these are very, very difficult things to actually implement with a single instruction. So the solution could be multiple instruction updates, but then they all require something like this, and you're going to see that this is actually the basis of hardware-based cache coherence. So once we get to this point, you might as well implement hardware cache coherence because it's much simpler. Okay, I mean, you can also flush invalidate all blocks in cache X, clearly, right? But again, that has the same problem. You may get rid of all of the blocks in your cache, but somebody else does a read right after that before you do the write. So you run into this race condition, and these race conditions are essentially impossible to prevent without hardware, in software without hardware support. So hardware needs to provide some atomicity, as we mentioned earlier. Okay, so you can keep brainstorming about this part. It's really interesting, but people have figured out that hardware-based cache solutions essentially greatly simplify software's job. And we're going to talk about that, basically. Anybody has any ideas on the software side? Maybe there's a magic mechanism that someone knows. But if you knew that, you could be rich. Okay, so hardware clearly greatly simplifies software's job, and this is another example of the programmer-architect trade-off. Again, if you get rid of hardware-based cache coherence, programmer's job is very hard. And we've seen that in real system examples. I kept giving the example of IBM cell processor many times, for example. It was designed without cache coherence, and it was very difficult to program plus compile into. And as a result, I don't think it's doing very well right now. But otherwise, it was a very nice design. It was the first heterogeneous multi-core, as we discussed. But if you have cache coherence in hardware, now the hardware architect's job is harder because you really want to do a good job over here. And one very simple idea is this, which is very similar to this Flush Global 8, actually. But you have a protocol right now in hardware that's running all the time. It's not directed by the instructions. It's running transparently to the software. Basically, you invalidate all other copies of block A when a core writes to A. Very simple, right? So essentially, this is a very simple coherence scheme. This is our first coherence scheme. I call it the valid-invalid coherence scheme. Cache as snoop, we're going to use that term, meaning that they observe each other's write and read operations. And if a processor writes to a block, all others invalidate the block. So you need to have, essentially, you broadcast a write to all other processors. And the protocol looks like this. Essentially, a cache block, this is the state of a given cache block. It could be in two states, invalid and valid. And it observes the actions from the processor, the local processor, because it's that processor's cache. And it also observes actions from the bus. It's basically the cache is connected to the processor on one side and the bus on the other side. Bus is really the rest of the system, and processor is a local processor. And for example, whenever a processor, if initially a block is in invalid state, and a processor reads that block, you transition into the valid state, and the cache sends a bus read request on the bus so that every other processor sees this read. Make sense? Then they can take an action based on that read clearly, right? Now, assume that you're in valid state. The processor reads that block, no problem. Basically, you can read that block without sending a message. Because valid state means that this is a valid copy that I have. Okay, if you write to that block, now you need to inform others. Basically, this processor writes to that block, a bus write signal is generated on the bus, and all other processors that have this block valid, when they see the bus write signal, they become invalid, as you can see. Right. Make sense? So this cache block exists in multiple processors, and they have different states clearly in different processors. Okay, so this of course makes some assumptions, right? What does this mean? Usually, whenever you specify a coherence protocol, you make some assumptions and you have some invariants. Now, this says something like if this block is valid and somebody, so you can infer things from here, right? And somebody writes to it, they generate a bus write signal, and in some other cache, this block is valid. You see the bus write signal, you become invalid. Make sense? But if you're valid, you read, if in any processor this cache block is valid and the processor reads it, it can read it and it can stay in the valid state. Make sense? So what is this assuming about the valid state? Any idea? Yes? Only one processor can write to it.
Yeah, can write to it.
Exactly. Only one processor can write to it. That's good. That's one invariant that you guarantee with this. But if you're in valid state, do you know whether this block is modified or not modified in the system compared to the memory? You don't know, right? Because you might actually read the block and it's valid right now, and it's clean, meaning that the memory has the same copy. And some other processor can do exactly the same thing, and it has the same copy. So it can actually have the clean copy everywhere. And when a processor writes to it, it still stays in the valid state, but everybody else becomes invalid, right? Now, when another processor reads that, hopefully it gets the right value. So for this protocol to work, you really need to have a write-through cache, and also no write-allocate cache, meaning that whenever you're writing to the block, you're also writing to memory, because some other processor is reading from the memory. Okay? That's the assumption here. So you can actually reverse engineer what your assumptions are about the cache by looking at the protocols over here. Sometimes you need to qualify your assumptions, of course. But basically, that's it. So that's one problem with this. If for this to work, in this case, valid means either shared or modified in one place. Right? And we're going to distinguish between that in a little bit. Hopefully this will become more clear. But basically, you design your cache and you design your coherence protocol. And in these state machines, we're going to see a lot of these state machines actually. The processor can take local actions on the block, processor read, processor write, that's the local actions. And there are actions that are broadcast on the bus for a given block, bus read and bus write. And we're going to talk about other actions also. Is this clear? It's a very simple protocol, right? Basically, the invariant is that whenever a processor writes to a block, it invalidates everybody else's blocks through the protocol. Okay, so this is hardware-based coherence. But let's talk about also, before we go deeper into this sort of hardware-based coherence protocol, let's talk about other non-solutions to cache coherence. I mean, you could also call these solutions, but I call these non-solutions really. Basically, no hardware-based cache coherence. Hopefully that's clear that if you don't need to provide hardware-based coherence, it's really the software's responsibility. And we said that this makes average programmers' life much harder. Now you need to worry about caches to maintain program correctness. I don't think that's a good idea. On top of this, not only you need to worry about it, but you also need to worry about the overhead that comes with it, right? So page protection, page-based software coherence, non-cacheable, all of those come with overheads, basically. Another solution is basically having no private caches. So coherence is a problem when you have private caches. Meaning if all of your cache is shared, there's clearly only one copy of the same data. Now, clearly there's no need for coherence if you have only one copy, but shared cache now becomes a bandwidth bottleneck in this case. And it's very hard to design a very scalable system with low latency cache access this way. Okay, maybe you can do a shared L1 cache for 4 processors. Even that's not done today. It's done with multi-threading, clearly. With hardware threads, you can share with 4 threads, you can share a cache. But with 4 processors, sharing the cache is hard because how do you place that cache now? What happens if you have 10,000 processors, right? Forget about it. It's not going to be a solution. It's not an interesting solution, basically, in the end. Okay, I think we already said this, right? Basically, you need to guarantee, so we're going to talk about hardware-based cache coherence mechanisms that do not assume any of this. Basically, we need to guarantee that all processors see a consistent value or consistent updates for the same memory location. This means that write to location A by some processor should be seen by some other processors eventually, and all writes to A should appear in some order. Now, this is a loose definition, but we're going to make it stricter later. So you need to really provide 2 things. One is write propagation. You need to guarantee that all updates that you do will propagate to other processors that will need the value. And you need to ensure that there's some sort of serialization. Basically, there should be a consistent order seen by all processors for the same memory location. Again, this is same memory location. That's why I like using consistent here, because it's the same order that everybody sees for the same memory location. So for this, you really need a global point of serialization for this sort of stored ordering. But again, you can think of this as you're serializing writes to a single memory location. Okay, the basic idea I've already given you. A processor or cache, you can actually use these interchangeably right now because we are assuming that a processor has a cache, and that cache can also take actions. It broadcasts its write or update to a memory location to all other processors. Another cache that has the location either updates or invalidates its local copy. So we're going to talk about this also. There are a lot of design choices whenever you design a coherence mechanism. Invalidation is one, but you could also broadcast the data value that you're writing, right? And everybody else can now update the location that the block that they've cached in their caches. And there are trade-offs associated with it, clearly. Okay, let's talk about those trade-offs. Basically, how can we safely update replicated data? So we can have an update protocol, meaning that you push an update to all of the copies that you have in the system. Or you have an invalidate protocol, which means that ensure there's only one local copy and update it. Right? Clearly, both are valid options. Basically, on a read, if local copy is invalid, you put out some request. And if another node has a copy, it returns the copy. Otherwise, memory does. That's what usually happens on a read. Again, you need to design the protocol to satisfy this. You can also say, I'm not going to get the data from some other node, right? You can say, I'm going to always get the data from memory. If you do that, then you need to ensure that memory always has the up-to-date copy. That's a restricting thing. And we will see that it's a restricting thing. Okay, on a write, it's more interesting, of course. But even on a read, you have design choices. Let me put it that way. Basically, you can, if you don't have the block, and some other cache has the block, you can get it from there. If memory has the block, you can get it from there also. If you're in a 10,000 node system and 200 of the processors have the block, you can get it from any of those 200 and perhaps the memory, assuming memory has the up-to-date copy also. Now you have a choice, right? Which one do you get it from? or who supplies the data? Now this becomes very interesting because assume that you want to minimize your latency, you want to get it from the closest location, right? But whenever you send a broadcast, someone needs to decide that they're closest to you and they send the data. Right? So there needs to be some protocol for that also if you want to minimize the latency in a large-scale system. And we'll talk about interconnects next week. So coherence, the scalability of your system and how you communicate between different cores, the shared data, is very much dependent on what your interconnect and what your topology looks like. Right? Because clearly, with some topologies, you have more nodes that are closer to you and nodes that are farther from you. In fact, it's very hard to design a scalable system that is uniform access between a point A to point B. Right? Okay, so this is definitely interesting, and we'll talk about that when we talk about interconnects more. But write is even more interesting now because when you read you need to do a write, you need to read the block into the cache as before, clearly. Now, if you're doing an update protocol, you write to the block and you simultaneously broadcast the written data and address to the sharers. Somehow you need to be able to do that. So one way of doing it is actually broadcasting the address and data on a bus or on an interconnect, and everybody else sees that address and data. And if they figure out that they have the address, they capture the data. Right? If they don't have the address, they don't capture the data. They leave it alone. Basically, other nodes update the data in their caches if the block is present. On the invalidate protocol, this is what we've been discussing earlier. You write to the block and simultaneously broadcast invalidation of address to all of the sharers. Okay, of course you need to have a protocol to guarantee that you don't have multiple updates to that location by different processors, right? And we will talk about that. And other nodes invalidate the block in their cache if the block is present. Okay. Any questions? Hopefully update versus invalidate is clear. But clearly this has trade-offs, right? Which one do you want? Whenever you write to a block, do you want to update all of the other sharers, or do you want to invalidate all of the sharers? Of course, there's a continuum in between, right? It's not black and white. You may update some of the sharers if you have some knowledge. But of course, that knowledge is very difficult to get. Anybody who wants to do an update to all of the sharers? You want to do an update? You want to say something, or you want to do an update? Do an update. Why?
Because if they are reusing the data, they will not miss.
Exactly, right. If they're going to touch that block or location again, they're not going to miss. In fact, touch that block. If you're doing it at the block granularity, they're not going to miss. But what if they're not going to touch that block? We might as well do an invalidate, right? Exactly, and that's the trade-off, basically. Basically, write frequency, how often you're writing to a location, and sharing behavior are critical. Basically, for example, if the share set is constant and updates are infrequent, doing the update gets rid of the overhead of the invalidates. Right? Essentially, if the sharers are touching the block and they're not necessarily going to update it, maybe it's okay to do an update, right? Basically, but for this, you need to know your communication pattern. Maybe what the update that you're doing is an update to a memory location that everybody is going to read after that. Then you may want to update. But if the update you're doing is to a memory location that's holding a lock, for example, and you're basically capturing the lock, maybe it's not a good idea to broadcast the update. You invalidate everyone, so no one else has the lock, and the next person gets the lock later on, right? So exactly. So basically, it's a trade-off. And the downside, as we also discussed, is if the data is rewritten without intervening reads by other cores, updates would be useless. So if this processor that has just sent, that has just got the coherence permission and updated the location, will do another update. We'll do another update, another update, another update, another update, another update before anybody reads it. Then you really don't want to send the data to all of the other processors, right? Because the first time you send the invalidation, everybody invalidates it. And if you design your protocol correctly or nicely, you also say, okay, now I have the only copy. I can do the update without informing anyone else. Right? The next update you can do without informing anyone else. The next update you can do it without informing anyone else. So invalidate is much better in that case, right? So it really depends on the behavior. Of course, there are many, many different types of behavior that we cannot go into. But if you know the behavior of a particular update, and if you can actually hint that behavior to the Coherence protocol, that actually helps. Actually, some ISAs have this sort of hints, coherence hints, like the Alpha ISA, which is a beautiful ISA, had these write hints, saying that I'm going to write to this location. And you could actually inform the hardware that you're going to write to that location, and maybe you're not going to read from that location later on with some instructions. And that instruction, if the hardware actually understands that instruction well, maybe it could choose between update and invalidate. Okay, so update, one of the other downsides of an update policy, at least an always update policy. If you always update, basically now you have a write through cache, right? If you're always updating, it means that all of your writes have to go through your cache. It's a write through cache. Okay, and must may become a bottleneck. Okay, invalidate, clearly after you broadcast the invalidation, the core has exclusive access rights if you design your protocol nicely. And now you can keep updating it without telling anyone. That's the beauty of this invalidation. And only cores that keep reading after each write retain a copy, in this case. That's also nice. But of course, the downside is if there is a lot of contention, if a lot of processors are updating the data, this can lead to ping-ponging. Basically, it can lead to a lot of invalidation and reacquire traffic from different processors. Okay, we'll talk about these a little bit more later on, but keep in mind that there is no best solution in the end. Ideally, you would like to be adaptive, but existing protocols are not adaptive enough. Most of them that are out in the field are invalidate-based, but update-based protocols partially exist as well. Any questions? Okay, I'm going through some of these relatively quickly, so hopefully you'll think about these offline. Okay, now let's talk about two cache coherence methods. So we talked about different design decisions, but let's talk about the methods also, because there are two major approaches to cache coherence. And these are the two seminal papers that I mentioned earlier. Basically, how do we ensure that the proper caches are updated? And when I say update over here, it could be an update or invalidate-based protocol. So one protocol is Snoopy bus-based protocol. Essentially, it was proposed by these two papers. It's assuming that you have some sort of bus. All of the processors see the requests that are put on this bus. Essentially, you have a single point of serialization for all memory requests. And the processors observe other processors' actions on this bus. Again, I say bus. It doesn't have to be a physical bus. You can actually have some sort of other interconnect. As long as you guarantee that there's a single point of serialization for all memory requests that everybody sees, that's fine. You can have a completely different interconnect than a bus. Of course, it becomes much more difficult to design. If you have a single bus shared by 16 processors, that's fine. Everybody sees that bus. But if you want to provide this sort of cache coherence across 10,000 processors, again, it becomes a bit more difficult. Right? So, okay. So, for example, processor 1 makes, we're going to add more terminology, unfortunately, but read exclusive request for a block A on the bus. Read exclusive means I want this block to be exclusively mine, and no one else should have the copy, because the implication is that I'm going to write to it. Right? And processor 0 sees this and invalidates its own copy of A. Right? I'm going to assume invalidate-based protocols from now on, but you can also apply this to update-based protocols. Okay, that's the idea basically. And that's completely different from a directory-based protocol, which was proposed earlier actually. Now you have, you don't have a single point of serialization for all memory requests. Whenever you send a memory request, it's not visible to everyone in the system. But you really need to, actually for coherence, you really need to guarantee this. You have a single point of serialization per block. And it needs to be distributed among the nodes. What does that mean basically? Essentially you have an intermediary between the processors. Here, you don't really have an intermediary because you have some shared medium. Once you say, I'm going to write to it, everybody else sees it and takes the appropriate action. Here, you go through an intermediary called the directory. Essentially, if you want to read or write to a block, you make an explicit request to a place called directory. And that directory tracks which caches have have that particular block. And directory basically coordinates the request such that you guarantee coherence. That makes sense, right? So clearly for this to work, I mean, this is fundamentally more scalable, clearly, because for this to work, you can have directory for block A in some location in the system. You can have a directory location for block B in some other location in the system. They don't need to be at the same place. Does that make sense? Because A and B have really nothing to do with each other from a coherence perspective. You're really keeping track of which processors have cached location A or B. They have nothing to do with each other, right? So these directory entries for these locations are different, and they could be distributed among different nodes. Okay, hopefully this will become more clear. But let's talk about the protocol first. Essentially, directory, everybody needs to go through the directory. So the directory has complete information as to where each block is in the system and who has what permission for that cache block. For example, processor 1 asks the directory for an exclusive copy. Again, that's the copy that it only wants. It says that I want this copy to be mine. No one else should have the copy. And the directory asks processor 0 to invalidate that copy because the directory knows that processor 0 has it. It waits for an acknowledgement and then responds to processor 1. Okay, so let's go through an example of this in more detail. This is easier to understand, I think, from my perspective, because you have an intermediary. And it's, in the end, fundamentally more scalable, but we will have trade-offs between these two different schemes. So let's assume that, basically, the idea is very simple. You have a logically central, I say logically central because physically it could be anywhere distributed, directory that keeps track of where the copies of each cache block reside. And caches consult this directory to ensure cache coherence, essentially. So an example mechanism, very basic directory-based mechanism proposed in that 1978 paper. For each cache block in memory, you store p+1 bits in directory. P is the number of processors, and you will see the +1. +1 is basically a bit saying that the processor has an exclusive copy. The processor that's indicated with its bit. It's a bit vector, basically. So basically, you have one bit for each cache. Again, cache and processor is interchangeable, indicating whether the block is in the cache. If the bit is set, that means that the directory knows that that cache has cached a copy. And the directory should know everything. And there's an additional bit, this +1. It's an exclusive bit. It indicates that a cache has the only copy of the block and can update it without notifying the others. So the directory can give this permission. Okay. On a read, what happens is the directory receives a request from the cache and sets the cache's bit and arranges a supply of the data. And we will see an example in a little bit. So the directory gets a read request and looks at its bit vector, figures out where the data is. It could be in memory. It could be some other processor's cache. It could be in both places and up to date. And arranges a supply of data. Now, arranges a supply of data is very general, clearly, right? I mean, you could do many, many things here. You could basically take the block out of memory and send it, assuming that's the up-to-date copy. You could tell processor X to send a message to the processor that requested the block, because that processor happens to be closer to that processor. So you could actually play a lot of games and optimizations over here, which is great, I think. So there's a lot of flexibility over here. So on a write, which is always more interesting, the directory basically gets a request calling write, usually read exclusive. Essentially, the directory looks at the bit vector for that memory location and basically figures out which bits are set. And those are the caches that have the block, and somebody else is requesting a read exclusive, which means that the directory sends an invalidate message to all of those caches that have their bits set in the bit vector. Makes sense, right? Now you don't need to broadcast invalidates to all of the processors in the system. You just need to send invalidates, multicast invalidates to the processors who have cached the data. So you can reduce the invalidate traffic that you have clearly with this. So if zero processor has cached the data, then clearly you're not going to send any invalidate requests. That's the beauty of this mechanism. Whereas with the Snoopy bus, you have to send invalidates, assuming you have an invalidate-based protocol. Okay, so basically it resets their bits. And clearly, it also sets this exclusive bit, and it also sets the bit for the processor that requested the write. So we'll see an example in a little bit with my nice handwriting that you're used to so far. Okay, so for this to work, of course, you need to have something else, which is really important. You need to have an exclusive bit associated with each block in the local cache, in each cache. Because how does the processor know that they have exclusive access to that block, right? Yes, they need to request exclusive access from the directory, and the directory says, yes, you have exclusive access, at that point, that processor knows, sets a bit with the cache block in the tag directory for the cache block, saying that, oh, I have exclusive access to this cache block. Next time I'm going to write to it, I'm not going to tell anything to anyone in the system, because directory granted me the permission that I can write to this cache block without notifying anyone. That makes sense, right? But you need to have that additional bit. If you miss that additional bit, your protocol will not work correctly. And if you're going to do optional lab 5, don't miss those bits. Although optional lab 5 is not really about directories, so. But you still need to have that exclusive thing incorporated in a state in the optional lab 5. Okay, so basically this enables the cache to update the exclusive block silently. It's a silent update, basically. Okay, so this is my handwriting that I promised. It's an example directory-based scheme. So basically, let's assume that this is the directory. The directory has a bit vector for a cache block. This is for block A. And we have 4 processors in the system, and we have an exclusive bit. And initially, all of those are 0, because no cache has the block. And because no cache has the block, no one can have the exclusive access to it. Right? So clearly, you have this for every single cache block in the system. Now you can see that this is a big structure. You can calculate if your memory is, I don't know, 1 terabyte. If your cache block size is 64 bytes, the directory is huge. It's 2 to the 30 divided by 2 to the 6, 2 to the 24 entries. And each entry is 5 bits in this case, because you have only 4 processors. Okay, this is a simple example. Because I don't want my bit vectors to be 10,000, right, entries. Okay, so let's take a look at an example. Processor 1 takes a read miss to block A. It sends a message to the directory saying that I want to read block A. Directory looks up the bit vector for block A, and it basically says, oh, no one has block A. And what does it do? It basically sets the bit for processor 1, 0, 1, and then reads the memory and sends the data to processor 1 for block A. Simple. Now assume that processor 3, now we're going to look at only block A. Processor 3 takes a read miss to the same block, sends a message to the directory saying, I want to read block A. And directory looks at the bit vector. Oh, it says processor 1 has the block, but it's not exclusive. So I have the same copy as processor 1. So processor 3 can also have the same copy. And the directory arranges that copy to be sent to processor 3. So, for example, it reads the memory and takes the block A out of it and sends it to processor 3. Now 2 processors have the block clearly over here. Makes sense, right? Okay, now the hairy part. Hopefully you'll be able to read it. If you don't read it, you can follow it. But basically, processor 2 takes a write miss now. So this was our processor. Okay, processor 2 is going to take a write miss. Go back here. This is our bit vector. What does the directory do? Processor 2 wants to write to this block. And processor 1 and processor 3 have already cached the block. So what does the directory need to do? First of all, the directory needs to invalidate these copies because somebody else is going to write to it. They're requesting read exclusive or write access. So it basically picks out the bits and sends the invalidation request to processor 1 and processor 3. And then, once those invalidations are done, usually these protocols are acknowledgement-based. Once it gets the acknowledgements that invalidations are done, it basically sets the exclusive bit and sets the exclusive bit for processor 2, as you can see over here. 0, 1, 2, yes. Make sense? You set the exclusive bit over here. Now processor 2 can update the block without notifying any other processor or the directory, right? Because once the processor does this, it also sends a message to processor 2 saying, now you have the exclusive copy and here's the data. Now do whatever you want to it. Make sense? Until I tell you you're not going to be able to do whatever you want to it. So the directory is really the mediator of everything. Okay, so as I said earlier, for this to work, processor 2 needs to have a bit in its cache indicating that it can perform exclusive updates to that block, clearly. So, and this is called a private bit or exclusive bit for cache block. It's private to this cache or exclusive to this cache. Both terms are used, actually. Okay, so now this is the state. Processor 2 is happily writing to this block. At some point, processor 3 wants to write to that block. Now the processor 3 needs to send a read exclusive or write request to the directory saying that I want to write to block A. Now what does the directory do? The directory, this is the state. for block A. The directory knows that processor 2 has exclusive access, and it has the up-to-date copy. Now the directory needs to send a message to processor 2 saying, give me the up-to-date copy and invalidate your block. You don't have exclusive access anymore. Right? And processor 2 hopefully obeys and gives the copy back. And now it doesn't have exclusive access. It doesn't have the block cached at all, actually, because somebody else is going to write to it, and the directory knows that. The directory now gives the exclusive access to processor 3 and sends the data that it got from processor 2. Makes sense, right? Now you're really optimizing the traffic. Of course, you have to go through additional latency to go through the directory now. So every access needs to go through the directory. That's the downside. Okay, we already talked about all of this. Okay, now if processor 2 takes a read miss, what happens? This is also a different action, actually. If processor 3 has the block exclusive, processor 2 wants it, but it doesn't want it exclusive. It just wants to read it. What does the directory do? Well, the directory says, oh, the up-to-date copy is in processor 3. It sends a message to processor 3. Processor 3, I want your copy, but you don't need to invalidate it. Just give up exclusive access. And processor 3, again, obeys. It keeps the data. And now that data comes to the directory, and the directory supplies it to processor 2. Now we're back into the shared state, right? Two processors have the same copy. And the copy was last written by processor 3 over here, when it had exclusive access. Yes?
Why does processor 3 need to give up exclusive access?
Because processor 2 takes a read miss.
Just taking a read, so the up-to-date copy can be sent and processor 3 can later on.
No. Then you will have inconsistent state, right? Because processor 2 wants the data, it's going to read it.
So that's up to that point, right?
Yes.
Later on, processor 3, and that's the latest value that processor 3 is sending.
But you don't know which value they will get, right? So that's the protocol. The invariance is that when you have exclusive access, only one processor can have exclusive access.
But processor 2 isn't asking for exclusive access.
Say it again?
The processor 2 doesn't need exclusive access, it just needs the latest value.
Okay. The problem is exclusive, by definition, means that you can update your copy without notifying anyone. So if processor 2 has a copy, and processor 3 has a copy, and processor 3 has exclusive access, it can keep updating it, and processor 2 will keep getting the wrong value. Right? That's the reason. That's why you need to maintain the invariant. If you had some other definition, then that would be different. But exclusive in general means that you have exclusive access and you don't need to notify anyone in the world. If you define it that way, then yes. Then you have to maintain that invariant. Makes sense, right? Okay, so I've given you an example of different types of operations. You can come up with maybe other operations over here. We're going to get back to the directory later on. So the directory actually is a very flexible, it enables very flexible optimizations in the end. It's really the coordinator for all actions to be performed on a given block by any processor in the system. It guarantees correctness. It guarantees ordering because everybody goes through the directory. Yet there are many, many opportunities for optimization, as we will see. We'll see some of them. We'll clearly not see all of them. And people have optimized these a lot in real systems. For example, you can potentially bypass the directory sometimes, directly communicate between caches. Assume that, of course, you need to design the protocol to make sure that that happens. We may talk about that. And we'll see examples of some of these optimizations later. By the way, this is employed in scalable systems. Whenever if you want to build a scalable system, you really need a directory-based cache coherence protocol. Existing systems employ a combination of Snoopy cache coherence protocol plus directory-based cache coherence protocol because with a small number of processors, it's easier to do Snoopy bus-based protocol. But once you need to scale up, you probably want to add some directory-based mechanisms into it. So it's really a hybrid mechanism that's employed in existing scalable cache coherent multiprocessors. Any questions? Okay, cool. So let's talk more about Snoopy cache coherence now. Basically, we talked about the idea already. All caches snoop, or all other caches read and write requests, and keep the cache block coherent. So to be able to do this, of course, you need to keep some metadata in your cache. So if you go back to the directory just a little bit, directory is keeping a lot of metadata to understand where the cache blocks are, who has the exclusive right. Also, the caches are keeping a little bit of metadata saying this exclusive bit, right, in each cache. Whereas in Snoopy cache coherence, it's only the caches that keep the metadata. Basically, each cache block has some coherence metadata associated with it in the tag store of the cache, of each cache. And we're going to see some of that metadata. It's essentially these state bits that we have, coherence bits or coherence state. This is easy to implement. Of course, there's also a state machine that updates that, as we will see. Basically, we're going to look at state machines for coherence. Clearly, this is easy to implement if all caches share a common bus. Essentially, each cache broadcasts its read and write operations on the bus. This is good for small-scale multiprocessors. But again, keep this question in mind. What if you want to have a 10,000 node multiprocessor, global shared memory multiprocessor? And we already know that some people claim that they have 400,000 cores, right, in a single wafer. You remember the Hardwarebased chip? In a single wafer, you have 400,000 nodes. Although, of course, they don't define what those nodes are, but today, a lot of things are possible, basically. In GPUs, you have a lot of nodes, right, if you consider all of those small streaming multiprocessors. Okay, so let's take a look at this, basically. This is what we're going to do. We have processors, we have a shared bus, that's the assumption. Assume that it's physical for now. We have cache, and we have metadata, coherent state, bits in the tag store. Okay. Each cache observes its own processor, as we discussed, and the bus. And it changes the state of the cache block based on the observed actions on the processor and the bus. And we've discussed that. So we're going to see some coherence protocols with some actions, for example. So we already said this, actually. Processor actions are processor read, processor write. Bus actions are bus read, bus write. But you can actually qualify this. Bus write is usually called bus read exclusive also. But there could be other actions also, as we will see. Sometimes, for example, you may send a processor may send a request saying, I want to invalidate other processors, but I don't need, and I want the data because I want to get the latest data. I want to invalidate other processors, but I don't need the data because I already have it. Right? That's another. You can distinguish between these different actions, whether you want the data or not also. Okay, we already said this basically. And we've already seen this very simple protocol. We're going to improve on this protocol basically. This is valid invalid protocol. Essentially, there's something missing in this protocol. Basically, what happens over here is whenever you want to write to a block, you always need to send an invalidate request. Right? There's no exclusive state, if you will, in this. Or, I mean, that's true. But actually, there's also not a modified state. That's why you need to actually, whenever you write to a block, you keep doing write through. So essentially, this is a state. This is invalid, clearly. In this state, you don't know whether you have the modified copy, exclusive copy, or the shared copy, right? Or the copy is shared. So we're going to extend that, basically. What if you want write-back caches? So basically, as a result of this, you need to have write-through caches. What if you want write-back caches? Essentially, you want a modified state. Clearly, this is. You can also actually tell that this is a write-through cache because there is no modified state over here. You want to write. You want to have a bit saying this is dirty, right? If you want to have a write-back cache, but you want a write-back cache because write-back cache has a lot of benefits in terms of bandwidth. So you really want to have a modified state. So a more sophisticated protocol essentially adds that modified state. We extend the metadata per block to encode 3 states. Invalid cache line is not present in this cache, it's obvious. Shared means cache line is one of potentially several cache copies, and it's clean. So basically, there's at least one clean cache copy, but you don't know how many exactly. So if a processor has the data in shared state, it doesn't know whether it has the only copy or whether there are other processors also have the copy block in shared state. And I'm harping on this because it's going to be something that we're going to fix in the next protocol. Okay, modified means shared cache line is the only cache copy and it's dirty, which means that you can actually write to this block without telling anyone. Essentially, modified means modified and exclusive in a sense. By definition, if you have the cache block in modified state, you also know that nobody else has it, which means that you can write to it without telling anyone. Nice, right? Okay. So what do we need to do basically? If there's a read miss from the processor, you make a read request on the bus, you get the data somehow, and you transition into shared state. Makes sense, right? Because either invalid goes to shared. When you get a write miss, you make a read exclusive request on the bus, and everybody else somehow invalidates because of the protocol, and essentially you transition into the modified state, and you can keep writing to that block without telling anyone. when a processor snoops read exclusive from another writer, from on the bus basically, it must invalidate its own copy if it has it, clearly, as we discussed. And this is an interesting part, basically, going from shared to modified. So you have the block in shared state, and you want to write to it. Essentially, you want to send a read exclusive request. In this case, you don't need to read the data from memory. Clearly, you have the data in your cache, one of the shared copies. You can basically write to it, but ensure that everybody else is invalidated. Okay. Okay, so this is the protocol, basically. This is from the Parallel Computer Architecture book by Color and Singh. I don't know if I really want to go through this in detail, but you can see some of the interesting parts, right? Basically, whenever you want to write to a block and you're in the shared state, this is interesting perhaps, you send the processor write, the cache will observe the processor write, and it sends a bus read exclusive request, and it's you go into the modified state. Now if you're in the modified state, and if you want to write to the block or read from the block, you don't need to tell anyone because that's the only cached copy, and it's up to date. Now if you're in the shared state, and if you receive a read exclusive, you invalidate your copy, and then clearly you don't need to send any other request. Okay, it's simple hopefully, right? As long as this works, that's good. Okay, so there's a problem with it, of course. Can anybody guess what the problem is? In the modified state, if you want to update the data, that's great. You don't need to inform anyone. Any guesses? No one? Okay, this is perfect. We should all go back to MSI protocols. Yes?
For read misses, you always have to ask other processors if they have it.
Yes.
So even if there's no coherence, or if there's no accesses to the shared memory, you still have overhead.
I see. Let me see if you're getting at what I have in mind. So when you do a read, you get the data, and you're saying basically if no other processor has access to it, you still need to ask whenever you want to write to that location. You still need to ask the others.
Yeah, so I'm just thinking about a situation where no caches go to the same memory location, and then this would still have overhead.
That's right. Exactly. Like, yes, and that's the problem. Maybe let me go into in more detail. Basically, on a read, the block immediately goes to the shared state. Right? You're reading the block, and you immediately go to the shared state. Although this may be the only copy in the system that is going to be cached. Right? So no other processor will ever cache it. Of course, you don't know it at that time. That's why the protocol is designed this way. But you can fix it, right? Basically, a block is in no cache to begin with, and only one processor is going to read it, and then it's going to update it. It has to go through some overhead, which is you get the data in shared state, and once the data is in shared state, even though it's the only copy in the system, it's in no other cache, if you want to write to it, then you need to basically ask other folks, meaning invalidate everyone else. But these are essentially useless invalidates that you need to send because you have the only copy. But you do not know that you have the only copy because the shared state semantics doesn't tell you that, right? The semantics is there's potentially, there's at least one copy in the system. It doesn't mean that there's exactly one copy. Make sense? Okay, so why is this a problem? Basically, suppose the cache that reads the block wants to write to it at some point. It needs to broadcast invalidate even though it has the only cached copy, essentially. And if the cache knew it had the only cached copy in the system, it could have written to the block without notifying anyone, just like I described earlier. Basically, it saves unnecessary broadcast of invalidation. It saves bandwidth and energy. So what do you need to do to help this? Basically, you add another state. Basically, if you want to actually optimize for coherence, you keep adding states. And here, now we have another state, which is MSI, and this is the idea on this Illinois protocol, basically. You add another state indicating that this is the only cached copy and it's clean. We didn't have that semantics in the state machine before, and it's called the exclusive state. Actually, I should, if you want to be precise, it's really clean, exclusive clean state. Because we have another exclusive state in the system, that's the exclusive modified state, right? Modified state is by definition exclusive, because you have the only copy. Here, we didn't have the exclusive clean state. meaning I didn't modify the data, but it's the only copy that, in the system, so I can modify the data without telling anyone. So basically, how do you actually get to this? Whenever you read a cache block, you place it into the exclusive state if no other cache has it while you're reading it. So you need to have some other, of course, some mechanism to detect this, right? Because you're reading the data. You're not doing a bus read exclusive. You're not doing a bus write. You're doing a bus read, really. At that point, you're not going to invalidate anyone, but you just want to figure out whether you're the only one who will have the copy. So you need some additional hardware for this. And the hardware could be this way, for example. You have a wired or shared signal on the bus. Whenever you send the bus read request to block A, all of the caches check their tag stores, and they basically assert the signal if they also have a copy. And because it's a wired OR, if you get a 1 signal, you know that at least one other cache has the copy. If you get a 0 out of this wired OR means that basically it's an OR, essentially. It's a big OR gate. You can think of it that way. Then if you get a 0 on that one, that means that no other cache has the copy, and you can set this block to the exclusive clean state. Make sense? Okay. So now you can do a silent transition to from exclusive to modified state when you do a write, because you know that you have the only copy. And this is the MSI protocol. It's also called the Illinois protocol, and I'd recommend reading this paper. It's a very nicely written paper. Its methodology is also interesting, actually. Okay. So basically, this is the protocol. You know these actions: processor read, processor write, bus read, bus write. Now we have actually there are bus invalidate and bus read invalidate. I'm going to distinguish between them in the state machine that's shown in the next slide. But basically, a bus invalidate means invalidate, but already have the data. Do not supply it or do not get it. Bus read invalidate means invalidate, but also need the data, because I don't have the data. Right? And now we have another state, which is exclusive. So exclusive is essentially, it's an exclusive copy and it's clean. Modified is exclusive copy and modified. Shared means shared copy and clean. And invalid is clearly invalid. And this is the transition, again, with my nice handwriting. You can see that we have this exclusive clean state now, and we have the exclusive modified state and shared clean state over here. Clearly, you can also have a shared modified, right? And that's probably the next optimization. But we will see that later on. Okay, let's take a look at an example. So this is the interesting part over here. Whenever you're invalid state, basically you don't have this block, but you want to read this block, you send, that's the processor read, you send out a bus read, and this bus read automatically determines whether this is the only processor that is essentially requesting the block. No other processor has the block. Essentially, that wired OR signal is 0. If that wired OR signal is 0, you can directly transition to the exclusive clean state. Now, once you're in exclusive clean state, when you do a processor write, you don't need to tell anyone. You just directly transition to the exclusive modified state. And if you keep reading or writing to the block, you don't need to tell anyone over here, clearly. If you keep reading the block, clearly you don't need to tell anyone over here also, because it's exclusive clean. But if you look, okay, I should really look at this also. Basically, if you're in invalid state, you read, and you send out a bus read. In this bus read, if that wired OR signal is 1, meaning that at least one other cache has the block, then you go into the shared clean state. That's the idea. So that's the beautiful, nice protocol. As I said, clearly you can have a shared modified state also, but then you need to modify the protocol, right? And that could have benefits, as we will see in a little bit. Okay, and this is the state machine from Coherence, and they have different terminology, as you can see. But it's the same thing, basically. On an invalid, if you do a processor read, and if it is shared, meaning that some other cache tells you that it has the data, then you go into the state. If some other cache tells you, no other cache tells you that they have the copy, you go into the exclusive state. And these are the highlighted parts that are really interesting. Okay, and if you want to do the optional lab 5, in the past people have done it. Actually, I used to have this in my undergraduate course at CMU, and this was a tough lab. But it's a fun lab also. Basically, we'll learn about cache coherence if you actually do it. You really learn about cache coherence by really implementing it. Because you will run into a lot of race conditions, for example, whenever you implement a cache coherence protocol, because you send a message and somebody else needs to receive the message, you need to do the update, all of that basically. You need to satisfy this plus potential race conditions. I mean, the reason I put it over here is to just introduce the lab, but also introduce some more terminology. I already actually introduced it. But basically, usually if you think about coherence, your permission levels go up and down, right, in a sense. If you're in the shared state, you don't have right permissions, clearly. You need to do something to get the right permissions. If you're in the modified state or exclusive state, clearly you have right permissions. So basically, a transition from a single owner state, exclusive or modified, to a shared state is called a downgrade. Because really the transition takes away the owner's right to modify data. You can think about it that way. Of course, the other way around, a transition from shared to a single owner state, exclusive or modified, is called an upgrade. Because the transition grants the ability to the owner, basically the cache, which contains the respective block, to write to that block. So you will see this downgrade and upgrade terminology also. Essentially, that's downgrade and upgrading your permissions as to what you can do to this block. And if you're in a single owner state, I like this terminology also. If you're in the single owner state, you can do anything to the block, essentially. Okay. Okay, you can look at that. And this is actually what Pentium Pro implemented. This is a slide from my advisor with his handwriting. Arguably, his is better than mine, I guess. But basically, this is essentially what Pentium Pro implemented in their cache coherence mechanism. It's the MSI Protocol. And it's the same thing, basically, what we've been discussing. Maybe there are slight modifications in the internals that they don't tell everyone, but MSI is a protocol that was implemented. But existing protocols are more sophisticated, actually. So let's talk about some trade-offs. We'll take a break sometime soon. Let me see. Should we take a break? I don't know. Yeah, we should probably take a break. But let's talk about some of these trade-offs, because I think this is really the time to really introduce the next thing. So basically, there are multiple questions. Should a downgrade from modified to shared, modified go to shared or invalid? That's a question, right? Modified means you have the block at exclusive state, you're modified, it's the only copy in the system, you're downgrading it, meaning that somebody else requested the block. Should you go to the shared state, or should you invalidate the block? Well, this depends, right? You should go to the shared state if the data is likely to be reused before it's written by another processor. Because somebody else is not requesting a read exclusive request. Somebody else wants a read. They want the copy, but they're not going to write to it. So you have a choice now. You either go to the shared state, or you go to the invalid state. If the data is likely to be reused by this processor, who has to make a choice, maybe you go to the shared state, right? Because you're going to read it again before somebody else writes to it. But if you're not going to reuse the data before somebody else writes to it, then you might as well go to the invalid state. Right? So you have a lot of choices, actually, even in a simple protocol like this. You can do cache-to-cache transfer on a bus read. Should data come from another cache, or should it come from memory? Who should supply the data, basically? So another cache may be faster if the memory is slow, or if it's highly contended. And usually memory is slow, as you know, but if the other cache is also contended, then it may be slow. But memory can be simpler. Essentially, there's no need to wait to see if another cache has the data first, and also which cache should supply the data, because you have a choice over there also. You create less contention at the other caches. But if you want to get it from memory, you require a write back on M downgrade. What does this mean? This may sound cryptic, but basically, if you're modified, you have the only copy, and now you're downgrading it. Now, downgrade means that this is going to go into shared state, and you need to write the data into the memory, right, if you want to be able to read it from memory. And actually, the shared state semantics require that, in a sense, because shared state means shared clean, by definition. If you want to fix this, you can have a shared modified. Shared modified means there's at least one copy of the data in the caches, and it's modified, meaning that memory doesn't have the up-to-date copy. But we don't have that state in the MSI protocol. Okay. So basically, is the write back on modified to shared necessary? It is necessary in the MSI protocol, actually. So how do you fix it? Well, you can add another state saying that maybe you have modified and shared. This is not exactly doing what I just said, actually, but one possibility is to add an owner state. This is called the MSI protocol. One cache owns the latest data. Memory is not updated. And memory write-back happens when all caches evict the copies, basically. Okay, anyway. So basically, let's talk about the problem with MSI. Shared state requires the data to be clean, essentially. All caches that have the block have the up-to-date copy, and so does the memory. That's really the definition of the state. Which means that you need to write the block to memory when bus read happens when the block is in modified state. Because you have to maintain this invariant, right? Otherwise, you violate the semantics. And once you violate the semantics, you can get the data from the wrong place. Essentially, you need to write when you're in modified state and when you observe a bus read, you need to write the data back to memory so that you go back to the shared state or you go back to the invalid state and memory has the copy. Right? Makes sense. So why is this a problem? Clearly, memory can be updated unnecessarily, right? Some other processor may want to write to the block again. So you're in modified state. Some other processor requests the data. Now you write back the data to memory. You also supply it to the processor, let's say. Now that processor has the data in shared state, and then later it basically says, I want to write to that block. It writes to that block. It's in modified state. Now the memory got updated for no reason, right? Because that processor updated the data before nobody else touched the data. So you could keep doing this, basically. You could have a lock, for example, in your caches. It can go from modified state to invalid on this cache. You update memory when it goes to invalid. And you supply to the other cache that wants to write to the lock. That lock becomes modified over here, and you update memory. And then some other cache wants that. And that gets invalidated. You write back to memory. Basically, this is the ping-ponging effect amplified because you keep writing back the block to memory, even though that write to memory is really not necessary. Does that make sense? You need to think about this a little bit, of course. But basically, this is a problem with, again, the semantics of the state. And semantics of the state is important because that enables you to design the protocol in the end. So basically, how do you improve this? Clearly, once you understand the problem is really you're updating memory unnecessarily because the shared state requires the data to be clean. Essentially, how do you improve? Well, first idea is do not transition from modified to shared on a bus read. Invalidate the copy and supply the modified block to the requesting processor directly without updating memory. That is essentially you change the protocol a little bit, right? This way you don't add a state, clearly. But of course now what happens is you transition from modified to invalid, and the other processor transitions from invalid to modified. Does that make sense? Because modified means you have the data, you have the up-to-date copy, nobody else has the copy, so you have the most up-to-date copy. Somebody else wants to read it. Now that somebody else is going to get the up-to-date data directly from you, and nobody else will know it. That's the idea, basically. That somebody else goes from invalid to modified directly. That's the idea. You could modify the protocol this way, and it's not an unreasonable way of doing it. But of course, is this really necessary? Because it's a bus read, right? So there are trade-offs associated with it also. Maybe that other processor doesn't need to write to that location, because now it has the exclusive data, and somebody else may need to get the data in some way. So you keep modified data traveling around. It could actually be a good solution for this ping-ponging of the locks. So the second idea, which is actually this is also implemented in some processors, but this is also implemented in some processors as well. Essentially, you transition from modified to shared, but designate one cache as the owner. And that owner will write the block back when it's evicted. So now essentially you have a shared, now your shared state, you kind of redefined your shared state. It's shared and potentially dirty. Right? Which again may or may not be the best thing to do, depending on your sharing patterns. Now shared means shared and potentially dirty, and this is a version of the MSI protocol. There could be other versions of it. So with one cache has special status in this case. It's the owner of this cache block. If it's in the O state, it knows that the data is shared, and it's dirty because it's owner, and it needs to write back. And that's the only cache that knows that it's the dirty block. All other caches, if they see this S state, they basically don't know if the data is dirty. Which makes sense, right? With this protocol. Is that a good thing or a bad thing? Yeah, we can you need to think about it depending on sharing patterns. But clearly this fixes the problem that we talked about now. Modified state, shared state is not only clean, it's really potentially dirty. And you know which cache is going to write it back. Of course, now if this cache that has the data, that has the block in O state, it needs to evict the data, there needs to be some special action, right? It needs to write back the data. But the shared caches don't need to be changed. That's the good part. The caches that have the same block in shared, they already have the up-to-date copy. Okay, basically, I think the takeaway is the protocol can be optimized with more states and even more prediction mechanisms, because you can actually predict what's going to happen to the block, and based on that, transition between states, right? You can predict whether some other process is going to update it or invalidate it or going to read it or write to it, or what is the write frequency that you're going to see. There are many, many potential optimizations that have been proposed in literature. It's very interesting, but you could get bored reading all of those things. It's fun to read, but at some point you say, okay, how many more of these optimizations that you're going to do? But the downside, of course, upside is you reduce unnecessary invalidates and transfer of blocks, but you keep adding more states and optimizations. And I think the big downside is it becomes more and more difficult to design and verify, because this leads to more cases to take care of, more race conditions to ensure that these things are done correctly without one processor going into one state without any race condition, of course. And in the end, of course, they provide diminishing returns also, right? Going from valid invalid to MSI provides a lot of return. Going from MSI to MESI provides a lot of return. Of course, in workloads that have that behavior. In some workloads that you don't get return. Going from MESI to MESI provides some return, but it's diminishing over time. Okay, so this is a good place to stop, because we're going to compare these two cache coherence methods now. So let's take a break. Let's see. Let's be back by... So now you've seen two methods of cache coherence with a lot of potential trade-offs. Let's compare these two at a high level. So Snoopy bus and directory-based, right? It's also called Snoopy cache, not to be confused with Snoopy the dog. Okay, basically, if you look at the Snoopy bus protocol, Snoopy cache protocol, here the miss latency or critical path is short, right? Whenever you get a cache miss, you get a bus transaction to memory, you don't need to go to an intermediary like the directory, right? That's the big advantage of this. This is much faster to satisfy. You don't even need to go to the memory, right? In some cases, if the caches have the cache block. Global serialization is easy. Bus provides this already because of the bus arbitration. If you have a single bus, it's really easy. But we said that for this very reason, this is also not very scalable, right? And we will see that. And again, Snoopy cache is simple. You can adapt bus-based multiprocessors easily, and essentially that's how things started scaling, right? You had one single processor, and people had one more processor, another processor. I think Pentium Pro, for example, it was 16 processor, 16-way multiprocessor, and you can have a bus-based multiprocessor that way nicely, a single bus shared across 16 processors. But if you want to go beyond that, now your bus becomes a bottleneck, as we will see in the next lecture in interconnects. So once the bus becomes a bottleneck, Snoopy cache becomes, its performance degrades. But of course, there are downsides to it also. Basically, every request is a broadcast message essentially now on the bus. And this is by definition of the protocol, you rely on broadcast messages to be seen by all caches in the same order for a given cache block, clearly. So you have a single point of serialization, bus. It's not scalable. In fact, as we discussed, this point of serialization is too strong, right? Meaning, you don't need to, essentially you have a single bus, it's a single point of serialization for all requests to a given memory block. Yes, that's true. But it's also a single point of serialization to all requests to all memory blocks, right? So it's unnecessarily strong in a sense. So if you could do this across multiple buses, you could potentially do it. If you have multiple buses, now you could communicate half of your memory on one bus and the other half on the other bus. Essentially, you could divide the coherence traffic on these two buses, right? That's possible to do, but we normally don't have that. Of course, when we talk about interconnects, you will see that. But essentially, this is not very scalable. So in order to be scalable, you need a virtual bus and have a more scalable interconnect underneath, and somehow totally ordered interconnect. But we're not going to talk about that right now. it becomes difficult to design, basically. So a directory, on the other hand, let's start with the downsides over here, because the downsides are going to be similar to the upsides over here. Essentially, we add indirection to the miss latency. Now you increase the critical path of every cache miss. The request first needs to go to the directory, and then needs to go to the memory, and then go back to the processor itself. So clearly, this is an additional overhead. But that overhead, that indirection actually helps scalability. This is actually very fundamental also. It's a fundamental rule of life, maybe, right? If you don't have indirection, you have to do, you get low latency, but you're not scalable. If you want to be scalable, you add indirection, but now your latency increases. I think that's very fundamental again. So this requires extra storage space to track share sets. I think this really doesn't exist in Snoopy Bus because that's implicitly tracked. Although you do need coherence metadata. So here you need coherence metadata. I guess I should put that really. But I mean, you have to. This is much bigger than coherence metadata in the end. Although you need to actually. There's a past exam question in one of my exams. I don't remember which one. That compares the directory cost to coherence metadata cost, depending on your cache size, right? This depends on your cache size because cache blocks. If you have millions of cache blocks in your system, that coherence metadata in your caches could be high also, right? Okay. Interesting thing is this could be approximate potentially. So false positives are okay. For example, you don't need to have a bit vector for where you have one bit for every single processor, right? You can actually have a Bloom filter, for example, like we've discussed in the first lecture. You can approximate things, and people have proposed those things. As long as you don't miss invalidations, as long as you maintain correctness, it's not a problem, right? You can, for example, broadcast additional invalidations for caches that don't need, basically in cases where you really don't need those invalidations, that's okay for correctness. But if you miss some invalidations, that's a bad idea. So I can clearly optimize the size of this extra storage space here. And people have proposed that, especially if you want to build very large-scale multiprocessors, that's a good idea to do. Or we will see in a little bit that you could track that the share set in different ways, right? Do you really need to have a bit vector? Depending on your access patterns, maybe there's only one share at most. Then you don't need a bit vector, right? Maybe you have a linked list, a pointer basically saying that, oh, this is the only cache that has it, right? And then maybe you have some bit saying, oh, it has exclusive or not exclusive, right? Essentially, you can optimize this. But in Snoopy Bus, it's a bit harder to optimize the states because you need to add more states. Here you're tracking shares. Here you're tracking states per cache block locally. Okay, and here actually protocols and race conditions are more complex because you're really sending messages over here because you don't have basically the key reason for this is you don't have a single point of serialization across the entire system. You really have a fundamentally more distributed system in this case. And you can basically, you have a lot of freedom in the protocol. You can say, okay, this particular cache, send a message to this one, right? And you can direct that as a directory. And if you want high performance, you should actually do that. But then you need to be very careful when you do that. And if you're very careful, that goes against high performance. Why? Because you need to actually require a lot of acknowledgements in that case. What does being careful mean? Being careful means that you send a message to someone and you ensure that that message is received and the other processor acted on that message, which means that you wait for the acknowledgement before sending a message to someone else. So the protocol becomes more complicated, more slower because you need to have a handshake and the overheads increase and you need to maintain correctness in the end. But of course, the big downside is, I think this could also be seen as an upside. You can have very complex protocols over here, whereas it's a bit harder to have more complicated protocols over here because you need to require broadcast. Basically here, you can have complicated protocols over here, but maybe you don't have as much flexibility in those protocols. So the big advantage of directory is it doesn't require broadcast to all caches. Right? There's no reason to do broadcast to all caches. You basically send as many invalidations as you really need. But of course, the downside is you have to go through the directory. And it's exactly as scalable as the interconnect and the directory storage. Here, you're as scalable as the virtual bus, let's say. Here, you're exactly as scalable as the interconnect that you built, which is very nice, I think. Then you can scale to tens of thousands of nodes. And of course, the directory storage. But the good thing about directory storage is you don't need to have it in a single place. Assume that you designed a multiprocessor with distributed shared memory. Then you can have it anywhere you want, right? Okay, I'll put some examples here. These are nodes, different processors, and basically this is memory. I guess processor, memory. Imagine that you have, I don't know, whatever, tens of thousands of these. Essentially, this is your directory, right? And your directory is distributed across the memories. So, I don't know, you can distribute your cache blocks across these memories, or pages, or regions. For example, memory region going from address 0 to n-1 is here. Maybe n to 2n-1 is here. And then 2n to 3n-1 is here. And you can keep doing that, right? And you exactly know which directory to consult if you're trying to access a cache block that's within this region. Now your directory is completely distributed across the system. So there is no single point. You don't have a scalability problem with your directory, basically. You're as scalable, again, as your communication substrate, which is the interconnect over here, because now you have tens of thousands of nodes. How do you get this message from this processor to this directory node, maybe that's over here, right? If you're accessing that particular location in the global shared memory. Make sense? Okay. But that's the beauty of the system. Okay, but clearly this is much more scalable than a bus because you cannot put tens of thousands of nodes in a single bus in the end. Okay. What's happening over here, you think? Somebody's messing with my directory. Okay. Anything else over here? Any other thoughts? This is exactly the reason why we covered coherence before the interconnects lecture. Interconnects become much more interesting once you cover coherence first. Okay, so let's revisit directory-based cache coherence a little bit. I'm not going to spend a lot of time, but I'm going to give you some example optimizations that you can potentially do. I'm going to skip this because we already talked about this. Basically, you have a bit vector to keep track of the shares. But basically, these are essentially, I would call them required when you scale the capacity of a single bus. Let's say 16, maybe 32 processors. Because it is distributed, essentially coherence still requires single point of serialization for write serialization, but the serialization location can be different for every block, just like what I drew over here, basically. You can, the blocks can be striped across nodes and memory controllers, or you can have some data mapping mechanism between the memory controllers or directories in the system. But the other interesting thing that the directory-based protocol provides is, now you can reason about the protocol for a single block. You can think of it as this is essentially message passing, right? You're really sending a message to the directory, and you're getting permissions. Essentially, the directory is the server, and private caches or the processors are clients. They're requesting permission. Right? Directory receives messages or requests from the clients, reads and read exclusive, and sends responses to the clients, invalidation requests. Invalidation in this case is explicit as opposed to Snoopy buses. So this may be easier to verify protocols with. Okay, of course it's not just invalidation requests. You could do other things as well, like we will discuss. Okay, before we go into those other things, let's talk about data structures. I mentioned this briefly earlier. Basically, a directory needs to keep track of who has what block and what state. Right? In the basic directory mechanism, we showed the bit vector. And we showed an additional bit for exclusive state. Essentially, you need to encode information about each cache block. And this is required to support invalidation and cache block requests. And key operations, you need to basically have a set inclusion test. Basically, what do I mean by this? You need to figure out whom to invalidate, let's say. Whom to invalidate, if you have a bit vector, is easy. You basically scan the bit vector, figure out which ones have the bit set, and then send invalidation messages. But you don't need to encode things that way. You can actually encode things much more compactly with some false positives allowed. Right? Meaning that you have, let's assume that you have a Bloom filter, and you just need to encode which caches may contain the copy of the block. Right? You don't know exactly if they contain, But you should ensure that if they don't contain, if they contain the block there, and that they're encoded. That's the idea. And you send invalidation messages, maybe with some false positives, and the caches that receive additional invalidation messages when they don't have the block, they basically ignore that invalidation, right? The directory, so if you have a balloon filter, you may actually invalidate 100 caches as opposed to 1, because your bit has encoded 100 of those caches. So you have 99 extra invalidations. It's still better than the 10,000 you would do in a bus-based protocol if you have a 10,000 node system. It's not as good as 1, clearly, but your directory directory data structure can be smaller, right? Clearly. Okay, and false positive rate in the end determines your performance. So you don't want to do too many of these invalidations still. So clearly, most accurate representation is full bit vector, but depending on the size of your system, you may not want that. We'll have an exercise about that in a little bit, maybe. So people actually look at compressed representations. They compress the bit vectors sometimes. If you have a lot of zeros in the bit vectors, you can compress them relatively easily. You can have a linked list representation. If you have few shares, for example, we can have basically pointers, right? IDs of the nodes that contain this node. In what state, right? Or you can have balloon filters. Those are all possible, basically. Is this interesting? And clearly, if you have a directory, there's another thing that is not in the slides, but your coherence granularity can be changed as well, right? Do you need to really do this on a cache block basis? You can actually do it on a coarser grain basis, and maybe even a finer grain basis as well. Although finer grain is a bit harder, right? Because if your caches don't operate at a finer grain level, you cannot invalidate at a finer grain level, right? If you have sub-block caches, you could do that potentially. But why am I talking about granularity? Granularity is interesting because if the granularity of coherence is larger than the granularity of updates, you always have the problem of false sharing. Now, what does false sharing mean? Basically, the two processors or two caches work on the same cache block, but they don't really share data. This is possible, right? Because cache block is 64 bytes. One processor is updating the beginning 4 bytes. The other processor is updating the end 4 bytes. They have nothing to do with each other, except they happen to be in the same cache block. This is really bad, because if both processors keep updating those 4 bytes that have nothing to do with each other, they're in different parts of the cache block, you will get all of the invalidation messages, and you will keep ping-ponging for really no reason. It's physically, you really don't share data, or semantically you don't share data, but because of your granularity of coherence tracking is larger than the granularity of your updates, you run into this false sharing problem. The sharing is not real, it's really false. And this happens in real systems. So how do you solve the false sharing? Well, one way is reducing the granularity of your coherence. Well, if you reduce it to 4 bytes or 8 bytes, you have a different problem, right? Now you have even more things to keep track of in your directory. And also in your caches, now if your cache blocks are, and now if your coherence granularity is smaller than your cache block, you need to add additional state in a sub-block level. Now if you have a sector cache or a sub-block level cache, it could be okay, but still it's additional state. So basically it decreases complexity. As you go finer and finer grain, your complexity increases and increases. Your false sharing clearly reduces and reduces. That's good. Today, most cache coherence protocols operate based on cache block level, but people have proposed coarser grain methods also. So coarser grain methods can be useful because those reduce your state. Right? Let's assume that you do this not on a cache block basis, but on a page basis. Again, it's not software based, it's hardware based. Hardware basically ensures coherence, but this is at the 4 kilobyte granularity. Now, this increases the probability of false sharing, of course. That's a bad thing. But this reduces the probability, this reduces the complexity of coherence tracking. Now, right now, the structure of your directory, it doesn't need to keep track of 64 byte locations, it keeps track of 4 kilobyte locations. So there's always a trade-off between storage and performance. In this case also, actually, you add additional storage, you get better performance because your false sharing reduces. But you could also reduce the storage that you have and increase the false sharing. Of course, if your application doesn't have this false sharing problem, then it's not a problem, right? Then maybe keeping track of coherence at a coarse granularity is okay, as long as you don't run into more false sharing. So granularity is interesting in the end. And whenever you have this sort of thing, granularity is not easy to optimize also. So because usually you want flexible granularity. But flexible granularity is also not easy to get, because your hardware structures are not flexible in terms of granularity, right? And people have tried to get hardware structures that are flexible, that can keep track of multiple granularity things, but it's not easy to design these things. I mean, a real example is a TLB, right? A translation look-aside buffer, a virtual memory system, has multiple granularity pages in today's systems. You don't get just 4 kilobyte pages, you get 1 megabyte, and sometimes you get 1 gigabyte, huge pages, right? You get small pages, large pages, and huge pages. And these are 3 different granularities. And TLBs are not very flexible. If you go and read the manual for the latest Intel processor, they will tell you can have only 2 or 4 huge pages. But you can have 512 small pages. Something like that, basically. You can read the manual. I made up these numbers. Clearly, I don't remember exactly what those numbers are, but basically they're not flexible. That's the takeaway. Because the hardware is not flexible to satisfy all those granularities. That's a good research problem to solve, but it's not an easy problem to solve also. Okay, so I wanted to mention that before we move into directory. So directory has, actually the semantics of directory is really similar to a snoop-based system. In the end, there's a higher level thing over here. You have a protocol. That same protocol can be implemented on a snoop-based system, also in a directory. And you can, basically these are 2 different ways of, that's why I call these mechanisms, coherence mechanisms. I didn't call them coherence protocols. Protocol could be MESI, MSI, valid, invalid, Moesi, or whatever you come up with. That could be implemented on top of a snoop-based system or on top of a directory, and you can do it. Directory is clearly capable of implementing any protocol that you can come up with, right? Snoop-based system is also because you need to architect it that way. But of course, directory does it with explicit request and reply messages. And I guess we've seen some of the requests. I'm going to show you some examples in a little bit. That's why these are here. Basically, directory receives read, exclusive, and upgrade requests from nodes and sends invalidation and downgrade messages to shares if needed. It forwards requests to memory if needed so that the memory can bring the data, and replies to the requester and updates the sharing state. Basically, these are the basic directory messages. But protocol design in the end is flexible. Basically, exact forwarding paths, like who gives the data to whom, depends on the implementation. Again, directory is the orchestrator. It can tell any node to do anything. For example, you can do cache-to-cache transfer rate. So let's take a look at some examples over here. These are actually examples from Coherence Sing book. They have more examples if you're interested. So for example, a processor 0 wants to acquire an address to do a read. It basically sends a read request to the home directory for that address. Basically, every address has a home node, in this case. That's where the directory entry for that address resides. So the directory is really distributed. You can have actually, these are nodes, and you can have tens of thousands of nodes, circles over here. And the home for a given address could be in any one of the tens of thousands. But you know that mapping, basically, whenever you generate the request. And you send a read request, and the home node sends the data as exclusive or shared, depending on whatever it wants to do. But it doesn't need to send the data this way. Maybe the home node knows that the data is really in processor 1, and it sends a request to the processor 1 saying, processor 1, please send the data as shared to processor 0. Right? So you can definitely do that, this sort of optimization. So you can do read exclusive with former owner. Former owner means somebody else is owning the data right now. So let's assume that this processor wants to write to the data. It sends a read exclusive request to the home node. And the home node basically knows that somebody else has the data, so it sends an invalidation request to the owner, and owner supplies the data with a revision. It's called a revision in this particular book. And then the home node, and also it could supply the data directly to processor 0 in this case. I mean, it could also supply the data over here, and then it could supply the data over here as well, right? So this way, basically, this processor can get the read exclusive permission without the directory getting the data. Right? They can communicate directly with each other. The directory just orchestrates the transfer of the exclusive permission from P0 or from this owner, previous owner, to P0. Just change the bits, basically, without touching the data. It just needs to ensure that the data is communicated over here. Makes sense, right? They can play a lot of tricks, basically, because, for example, this owner node can be very close to this processor, right? And hopefully the directory knows that information also. Okay, so let's take a look at, there are other issues actually. This becomes more hairy if you have a lot of updates in your system. So let's assume that these two processors both want to write to the same cache block. They both send messages to the directory, read exclusive, and directory decides one of them will get the data in an exclusive way. So how does the directory decide? There are fairness issues associated with it also. We talked about fairness. There are other fairness issues related to coherence requests. And clearly, it needs to say something to the other one, or it needs to buffer the other one. In this case, we're adding something else to the protocol saying, okay, you get a negative acknowledgement, NAC. Then it's your responsibility to request the block again. Right? So this processor clearly is unhappy in that case. This processor happy, but at some point, this processor requests the data again, and the directory invalidates data in the previous owner, and you get back the data somehow. Okay? So clearly this leads to fairness issues also. Basically, you can have contention in the directory. So what do you do with the contention? And you need to escape race conditions also. So if you have a lot of requests from different processors, you don't want to miss any requests. That's the key, basically, as a directory. So you can NAC the requests by saying, well, I'm not going to give the permission to you, so I'll retry later. So the protocol needs to be designed that way. This requires the buffering to be done on the node, on the requester node, right? or the client, let's say. Directory is the server, other processors are the clients, and the clients need to do their own buffering because they have a request pending. They need it. The directory doesn't give them permission, so they have to request it again. Right? So buffering is pushed in the client nodes. But basic original requester retries in this case. Or the directory has some queue associated with it, right? And it basically queues the requests. This is similar to a memory controller queue. A memory controller does this for memory requests. Now the directory does it for permission requests, clearly. And it can have some algorithm to decide who it grants the request to, right? And it can be fair in that algorithm. Or it can have a combination, right? Because if you may need to have a huge buffer if you want to do everything in a queue basis or buffer basis. Once your buffer gets full or close to full, you can start NACing requests, right? Makes sense, hopefully. But I think this is, in the end, this is important. You need to resolve the contention somehow. And either way, queuing or NACing, you don't want to starve the different nodes. Because you could keep NACing the same node, right? Especially if a lock is contended. Remember the bottleneck acceleration lectures. If a lock is contended, many threads are requesting it. And if you're really at the top of the scalability point, probably some bottleneck is limiting your performance, meaning that you're really always at the contended point, potentially, depending on the application. At that point, basically, you have someone requesting the lock, and if you're not fair about it, you're creating some other bottleneck. Right? Essentially, this directory permission grant can be part of the bottleneck that you create in the system if you're not granting to the, let's say, limiter thread. Does that make sense? We talk a lot about bottleneck acceleration. If you don't grant it to a limiter thread, you may make the critical path of the program much longer. But clearly, existing protocols are not even aware of that today. Existing protocols usually use simple heuristics like, I guess, not even heuristics, first in, first out. That's not even scheduling, as you know. Basically, but it's simple, of course. But first in, first out is not fair, as you know very well also, right? Okay. So basically, fairness is a concern. Which requester should be preferred in a conflict? And actually, there are other issues affecting this now, because directory node is sitting somewhere over here. I know. Yeah, somewhere over here. This node is requesting read exclusively all the time, whereas this poo node over here is sitting over here, and it also wants the data. But this node has very fast access, clearly, to the directory, and you've got to be fair in that case, right? Because if you keep starving this node, it may become the bottleneck and limiter. But at some point, it needs to make progress, right? Okay, clearly internet delivery order affects these things also. Okay, so a lot of these things become worse if you not optimize your algorithms. If your algorithms require, basically lead to a lot of messages, a lot of synchronization, then the burden on your coherence protocol becomes much, much worse. So whenever you write a parallel program, if you haven't optimized it, if you cause a lot of ping-ponging, then your synchronization directly translates into all of these coherence messages. And then you're at the mercy of how good your coherence protocol is. Right? Because now you can see this difficulty, right? Basically, of course, ideally you would like to do the best at the software level and minimize the ping-ponging and all of that synchronization. But again, we know that trade-off, right? That trade-off now, you need to put a lot of effort into your software to reduce synchronization. Okay, any questions? I don't want to go deeper anymore. If you're really interested, you can read a lot of papers related to this. But also that Color and Singh has a very good treatment of cache coherence. That's a huge book like this, I think. It's a bit old. It doesn't cover a lot of new things, but still fundamentals are there. It was written in 1994. I don't think they ever published a second edition. Or maybe this was the second edition. I don't think they ever published the next edition, basically. Okay. So basically, there are questions over here. Scaling the directory. Basically, how large is the directory? I think I've given you some hints. How can we reduce the access latency to the directory? Any thoughts on this one? Because it's a bit cumbersome to go through the directory all the time, right? Yes?
Do you have rough numbers on like the ratio of the directory to normal memory access in terms of latency?
Well, it's essentially a memory access, let's say. You go to, because directory is sitting in some memory controller somewhere, and you go there, basically. And again, if you think about a large system at this point, it also has the interconnect latency to go to some other directory node. Any guesses? What can you do? If you want to cache the directory, maybe that's a good idea, right? And that's exactly what a lot of systems do. So if you want to reduce latency, caching is a good option, especially if you have locality. And people actually cache the directory, but I'm not going to go into the details of this. There are directory caches as well. Okay. But of course, you can imagine issues related to that also. How can we scale the system to thousands of nodes? This is more of a rhetorical question than a question that I expect the answer. And can we get the best of snooping and directory protocols? And as I said earlier, existing systems do both. It's for a local part of the system, you do snooping. And for the remaining parts, the bigger part, you do directory. And hopefully you map your application such that the local communication is maximized, whereas global communication is minimized. Okay. And heterogeneity is one example. There are also interesting solutions that are proposed in literature like token coherence, which I don't have time to go into, but maybe you can watch an earlier video of me that talks about token coherence. Okay, I'll talk about something else. Oh, wow. Maybe this doesn't want me to talk about anything, I guess. So these are, I don't know if I want to go through the exercise over here, but maybe we'll go through some of this. This is another an example. We will have a directory question in your homework. Maybe your exam too, who knows? These are actually nice questions. But this is actually a nice question that I like in a previous exam probably. Basically, assume you have a processor that implements a directory-based cache coherence protocol. The physical address space of the processor is 32 gigabytes, which is really small. And a cache block is 128 bytes. The directory is equally distributed across randomly selected 32 nodes in the system. You find out that the directory size in each of the nodes, 32 nodes, is a total of 200 megabytes. And now it's a reverse engineering problem. How many total processors are there in the system? Not that hard, right? In fact, who has solved it already? I'm just kidding. You need to do some calculation clearly here, right? But you can easily get this, right? Because you basically need to figure out how large is the size of your directory and how large is the directory in each node. And then, yeah. Okay, let's take a look. Basically, blocks per node. Basically, you can calculate this. They've given you the size of the directory, 32 gigabytes address space, 128 bytes per block, and divide by 32 nodes. Basically, each directory node needs to keep track of 2 to the 23 blocks. Makes sense, right? Basically, 32 gigabyte divided by 128 bytes is the number of blocks in the system. And they're distributed across 32 nodes in the directory. So basically, each directory node needs to keep track of 2 to 23 blocks. Now, we're also given the directory storage per node. It says 200 megabytes. Now, what is 200 megabytes? Divide 200 megabytes by 2 to the 23. It's essentially 25 times 2 to the 23 bytes. And essentially 25 times 2 to the 26 bits. Makes sense, right? Which means that what's going on here? Somebody's row-hammering my computer, I think, now. Okay, which means that the directory storage per block is this. You can get how many bits per block you're storing, right? This is given. So you know exactly how many bits is that. And that should be distributed over 2 to the 23 blocks, and each block has to have a bit vector, basically. So it's basically this divided by this, you get 200 bits per block. So now you know exactly how many nodes you have. 199, right? That's the idea, basically, because you have p plus 1 bits based on the protocol that we discussed in class. So that's a very simple question, actually. But that, I mean, it's interesting because basically, if you want to get 199 nodes, you need to have directory for 200 megabytes. Clearly, that was the forward engineering problem, which is easier to compute. But that's a lot for the size of a directory. And we don't even have a huge memory here. 32 gigabytes is nothing for 199 nodes, right? You really don't want to build a system like this today. 32 gigabytes, I almost have 32 gigabytes in this one. I wish I did, but this is 5 years old. But it's almost there, it's 8 gigabytes, right? Okay, so that tells you that actually this directory is huge in the end, at least in the way we described with a bit vector. Okay, any questions? Okay, if you have no questions, then I'm going to cover a recent example of cache coherence. This is based on a paper that we published in ISCA 2019. Essentially, this is coherence for near-data accelerators. Does that sound interesting? Okay, so let's talk about that. This is actually the earlier version of the paper. This is a new version of the paper. It's called Conda. And I'm going to use the slides that Amirali used. He's my PhD student at CMU for the slides. Basically, I mean, coherence is clearly, whenever you share data between any two components and they have caches, you need to keep them coherent, basically. It's nothing special to processors. Also, accelerators can have them. But I think the difference over here will be accelerators. Now we actually, in multi-core, we have a lot of cores, and coherence inside a chip is good. There are still scalability issues, but it's better than going off-chip. But if you have an accelerator that's off-chip, that's near memory, then you have to communicate with it. And if your goal with this accelerator that's near memory is to reduce data movement, you ship some functions to that near memory accelerator, and you hope that that accelerator doesn't communicate. But if you need to keep things coherent, you need to keep asking for permissions, right? Now that sounds bad, right? You design this accelerator so that you reduce data movement, but you're getting data movement because of coherence overheads. You don't want that, essentially. So I think it's a special problem with near-data accelerators because your goal is to reduce data movement, and you don't want coherence to be getting in your way in the end. And clearly, these specialized accelerators are everywhere. You can look at these nice pictures that I don't have my time to draw, but my student has time to draw. But the big challenge, I guess it's nice to draw these pictures because in the end they're good. Basic challenge is, maybe this computer thinks otherwise. Basically, the challenge is how do you provide coherence between these near-data accelerators that are in DRAM or in the logic layer of DRAM and the CPUs that are sitting on this side over here. Clearly, the problem is if you want to maintain coherence, if you keep exchanging messages like a Snoopy bus, you keep exercising that bus, right? So there's large cost of off-chip communication, which we wanted to eliminate in the first place. And these applications actually generate a large amount of off-chip data movement also. So this paper shows that it's impractical to use traditional coherence protocols, and I'll give you examples of this. So existing coherence mechanisms, basically the paper studies 3 major ones, and we will see them. We actually talked about all of them, but this will make it a little bit more concrete for some of them. They basically, if you actually use existing coherence mechanism, the benefits that you get from near-data acceleration, let's say with 3D stacked memory, get eliminated most of the time. With fine-grained coherence, actually, it stays there, but there's a lot of energy overhead. And it turns out the majority of the off-chip coherence traffic generated by the mechanism is unnecessary, and we will see an example of this. And much of the off-chip traffic can be eliminated if the coherence mechanism that you design has some insight into the memory accesses. Now we will see what that means. Basically, we're going to look at optimistic coherence in this case. If you ship a function to the main memory, that function will assume that it has coherence permissions. It's not going to do any coherence checks. It's going to execute, and at the end, it's going to record which blocks it has touched, and at the end, it's going to check for coherence. This is very similar to a lot of the optimistic concurrency ideas, actually, that have been proposed in the past, except it's tailored for near-data acceleration in this case. And when we get to it, I'll talk about transactional memory and examples of that also. But this is transparent to the programmer mostly. Okay. Basically, it's an optimistic approach. It gains insights before any coherence checks happen. But it basically optimistically assumes that you have the permissions and you perform only the necessary coherence requests. Okay. I'll keep going relatively quickly. But these are the key results. This is based on a conference presentation. So in a conference presentation, it's always good to foreshadow the key results after you give the problem and the basic idea so that people actually see what's coming. So basically, in the end, this comes close to the ideal NDA coherence mechanism that has no overheads. So what is ideal? You basically magically satisfy coherence without communicating, right? With zero-cost communication. That would be nice, right? And that's the ideal. You can simulate that ideal. That's the beauty of simulation. So let's go through this a little bit. So near data processing, you already know this very well. You move the computation close to data. There are a lot of benefits that we've seen with this. And clearly 3D stacked memory is one way of doing it, and that's what this paper evaluates. Essentially, we're going to assume 3D stacked memory in the logic layer. You can do acceleration. You can offload functions to the logic layer. And you've already seen this picture multiple times in different ways. So basically, this paper analyzes a bunch of applications. And these are actually interesting applications. You've seen some of them. Actually, you've seen both of them, I think. But graph processing and hybrid databases. And it turns out not all portions of applications benefit from near data acceleration. So some portion should remain in the CPU. Some portion should be accelerated in main memory. So these are some examples. Basically, memory-intensive portions benefit from near-data acceleration, but cache-friendly portions should remain in the CPU, right? We've discussed this already in the past also. If you have very good locality, maybe it's good to, and you don't have maybe it's good to keep things in the CPU. So as a result, you partition your application between the CPU and the near-data accelerator, and now you need to access the same region of data that the NDA kernels that are executed on the near-data accelerator access. And that leads to significant data sharing. And this paper analyzes some of those data access patterns and shows that even though these CPU threads and the NDA kernels share data, they do not typically concurrently update all of that data. Meaning, the data conflict rate is relatively small. So this is one example for one of the graph analytics applications. Only 5% of the CPU accesses collide or conflict with the near-data accelerator accesses, for example. You could argue that 5% is high. You could also argue that 5% is low. Basically, you just need to design a mechanism that takes advantage of that 5% in the end. I don't understand what's going on. Anybody? There is definitely a connectivity problem, but okay. Okay, basically, the takeaway, I think, is CPU threads rarely update the same data that an NDA is actively working on. So it's actually a lot of ways to satisfy coherence at every request, right? But it's not rare enough to ignore coherence also, because 5% is not 0%, clearly. Okay, so let's take a look at the analysis of existing coherence mechanisms. Basically, there are 3 existing coherence mechanisms. One is we talked about non-cacheable, which is not a solution to coherence, as I said earlier. And you will see the results with that. It's not going to be very good. Basically, the idea over here is NDA data, meaning data that's going to be touched by the near-data accelerator that you're going to operate in memory, is not going to be cached in the CPU. Meaning that whenever CPU needs to get the data, it needs to go to the memory. Now, that already sounds bad, because 5% of the access is updated, but there's some more the CPU may need to read it, right? Okay. The other one's coarse-grained coherence. We touched upon that also. Basically, this is more coarser-grained. Basically, you get coherence permission for the entire NDA region. Whenever you want to do something to data that's in the designated by the programmer as data that's going to be operated by one of the an NDA kernel, you basically mark your data, and some of the data is going to be operated on by the NDA accelerator. And you mark it, you know what that is. And whenever the CPU wants to access it, it gets permission to all of it. It's very coarse-grained. You don't need to get permission to every single cache line that you're touching. You say, whenever I'm going to access this region, I get permission to all of that. And you know the size of that region, which means that whenever the NDA accelerator needs to access that region needs to be flushed from the CPU caches, that entire region. There are multiple ways of implementing this actually, but that's one way. Okay, fine-grained coherence is essentially what we've discussed. It's a MSI protocol, for example. Very fine-grained. Whenever you want to update a location, you send a broadcast, and that broadcast goes through the off-chip memory bus. Right. Okay, so non-cache. Let's go through this a little bit more. Basically, you mark the NDA data as non-cache. So this all requires that some people know, or the programmer knows, what is NDA data. So what is NDA data? It's the data that's potentially touched by the near data accelerator, in-memory compute engine, basically. That's the assumption. But hopefully you know that. Okay, so clearly you have data sharing between applications that are running on the CPU, and between part of the application that's running on the CPU and that's running on the NDA. So this is a hybrid database, basically. In a hybrid database, you satisfy different types of queries. You have transactions that are more serial, that are doing updates to localized portions. And you run also analytics. Analytics is basically you look at a lot of data in your database and you want to basically mine some data. So this touches a lot of data in a more streaming manner, so it's very memory intensive. But here, transactions, you do a very simple update to a location, for example. Right? Like a banking transaction, right? You update your bank account. Whereas in analytics, the bank may be running some query on all of the bank accounts that everybody has. So it's really touching lots of data, mining data, doing something, whatever. Destroying your privacy in the end. That's another way of thinking about it, probably. And I'm sure they are. Anyway, but that's basically what it is. If you look at the characteristics of this is better fit for CPU. This is better fit for near data acceleration because it's very memory intensive. And it's relatively simple potentially, right? Transactions are not necessarily simple. But this leads to data sharing. Whenever the analytics is reading from a location that the CPU is updating, then you need to provide coherence. Okay, so, but of course, if the near data accelerator, whatever analytics is touching is non-cacheable, this is a really bad thing. Right? Because this is touching a lot of stuff. And you mark all of them non-cacheable. Whenever the CPU needs to execute a transaction on any part of it, essentially it gets a lot of cache misses, off-chip accesses. So this is not a viable solution in the end. It significantly hurts the CPU thread's performance. It's okay for this in-memory accelerator performance, but it significantly hurts the performance over here. And it's actually, if you look at this, there are results in the paper, but I'll foreshadow some of the results that I'm going to show also. If you have this mechanism, it actually performs 6% worse than CPU only. You did all the work, partitioned your application between CPU and near data accelerator, and now you have a non-cacheable coherence mechanism, and you get performance loss. Sounds terrible, right? You don't want this sort of stuff. You might as well not do any of near data acceleration. Okay, so coarse-grained coherence, it's going to be similar. Basically, you get coherence permission for the entire NDA region. So what does this mean? Whenever the CPU wants to touch data that's in the NDA region, it flushes the dirty data that is updated. So it may be a little bit better. I don't know. But this still leads to unnecessary flushing of large amount of dirty data, especially in pointer chasing applications. You can see the analysis of the paper. Or you can have, there are multiple ways of implementing coarse-grained coherence in existing systems. One is you flush, whenever you touch a region, you flush the dirty data associated with that region from your caches. The other way is using locking. You can say, whenever I'm operating on the region, I'm going to lock it, and the NDA accelerator cannot access it, and vice versa. That's the idea. So basically, if the CPU needs to access the NDA data, and the NDA data has the lock already, CPU needs to stop. You could do this at a coarse-grained level, clearly. Now, of course, this blocks CPU threads when they access the NDA data regions. So you either get the flushing traffic, or you get stalls. And it turns out, well, I don't know what happened here, but it fails to provide any performance benefit of NDA. You will see that in a little bit. Fine-grained coherence is what we've been seeing so far. Essentially, it has clearly fine-grained coherence is easy because you don't need to think about any of this that we've thought about, right? You don't need to mark anything non-cacheable. You don't need to deal with coarse-grained locks. It simplifies the programming model. And it also allows you to get permissions for only the pieces of data that's actually accessed. So non-cacheable and coarse-grained are not so good in that sense. But of course, I'm going to go through this. This leads to a high amount of off-chip coherence traffic. Basically, whenever the NDA region needs to touch something, write to something, it essentially needs to do a broadcast. And that's true for the CPU also. So you get a lot of broadcasts over here. And if you're doing a lot of writes, then you have a problem. And it turns out the analysis in the paper shows that fine-grained coherence actually is the best among the 3 previous mechanisms, but it still eliminates a significant fraction of the energy benefits of an ideal NDA mechanism, and still a good fraction of the performance benefits. Performance benefits are not bad actually, but the energy benefits are a lot of it is eliminated. So okay, so this is actually one graph. It doesn't include all the workloads clearly, but you can see this is CPU only. That's non-cacheable. This is the bar for coarse grain. This is the bar for fine grain. And you can see that non-cacheable is the worst. You can see that coarse grain is, okay, better than non-cacheable, but it's not what you want. Basically, you get the same performance as CPU only execution. Ideal NDA is, essentially, this is what you would get ideally when you partition the applications this way without any coherence traffic overhead. There's magic, clearly. Right? Basically, you get correct execution, but you don't have any overhead for coherence transactions. You can simulate this clearly. And ideal is more than, I guess, 70% over here, which is not bad. Actually, the paper has more results for large data sets. Large data sets, ideal is much larger. But for time reasons, the simulations take too long with large data sets, so most of the results are presented with small data sets. So when you go to large data sets, actually the numbers are much larger. Okay, but if you can see that fine-grained coherence is not bad, but it's not close. It's not very close to the ideal NDA. Now, if you go to the energy side, on the energy side, actually, this is normalized energy. If you look at the non-cacheable approach, it actually increases the energy compared to CPU only. That sounds bad. The coarse-grained approach actually reduces the energy, which is not bad. Fine-grained approach also reduces the energy, but not by much. And the ideal energy is over here, ideal NDA energy. So ideally, we want to get close to the ideal NDA, right, with a coherence mechanism. Your coherence mechanism should be lightweight enough that it should give you the performance and the energy consumption of ideal NDA. I'm going to skip these because this talks about whatever I said right now, I think. And you can look at the numbers. And clearly there are reasons for it, because you cause a lot of off-chip accesses. Okay. So what do you do then in this case, right? Basically, poor handling of coherence eliminates much of an NDA's benefits, and the observation is that the majority of off-chip coherence traffic is really unnecessary. And the goal is to design a coherence mechanism that retains the benefits of this ideal NDA and enforce coherence with only the necessary data movements, hopefully. Of course, in the end, you will still do some unnecessary data movements here, but we will hopefully minimize it. And the idea is to do optimistic execution. And you want to have insight into what's happening in the NDA region to eliminate the unnecessary coherence traffic. And you want to take advantage of the fact that, at least the empirical fact, that there is a low rate of data conflict between CPU threads and NDA kernels. And the idea is optimistic execution. What does this mean? The NDA executes the kernel, assuming that it has the coherence permissions for all of the data that's going to touch. And during that execution, it records or gains insights into the memory accesses. And when execution is done, at that point it checks. It basically performs only the necessary coherence requests. And if this check fails, meaning while you're checking, you figure out that, oh, you shouldn't have written to this location, then basically you roll back the NDA. You go back to a checkpoint. You go back to the beginning of the execution of the NDA kernel, or the function that was offloaded. Makes sense, right? And this is a fundamental thing. Basically, you're optimistically assuming that you have the permissions, you keep executing. If you figure out that, oh, you shouldn't really have done it because CPU conflicted with you, you go back. This is actually very similar to a lot of transactional memory approaches. And the transactional memory approach is very similar. If you think about transactional memory, what it says is you're protecting shared data. And as opposed to protecting the shared data with locks, you say you protect it with transactions. And transactions encapsulate the regions that you're supposed to have mutual exclusion on. So what transactional memory provides the programmer with is you execute a transaction and you start. It's optimistic concurrency. Basically, you start the transaction optimistically, assuming that you have the permissions. Basically, you don't lock. You get rid of the locks. It's a transaction. And you record which blocks you've touched in this transaction. And the other transaction that's executing on some other core also records what other blocks it's touched. And at the end of the transaction, you compare if any other transactions conflicted with you. Makes sense, right? And we will see one example of how you compare. If no other transaction has conflicted with you, you're done, right? No problem. You can commit to everything you've done. If somebody conflicted with you, you have to go back to the beginning of the transaction. And again, the reason people have proposed this was you have, well, there are multiple reasons, but one of the reasons is whenever you're doing shared data accesses, the programmers need to be conservative. Basically, they have a lock because they don't know which other thread is going to update that location, or if they're going to update that location, they're conservative. But these two threads that are executing on a shared data structure, they may be updating totally different portions of the data structure. If their updates don't conflict with each other, there's no problem, right? Locking is actually very conservative from that perspective because it allows only one thread to execute and then the other thread to execute. But if you have transactions, both of these can be executed simultaneously, and then both threads can be in the critical section, but it's okay as long as they don't conflict with each other. That's the idea. So this idea is very similar to that, but from the NDA perspective in this case. So basically, it's also called optimistic concurrency in the end. So you have the CPU thread that executes. It launches a function on the near data accelerator, and that's an optimistic execution at that point. And that optimistic execution assumes that it has the permissions, and these two execute concurrently, happily. There's no coherence request. And at the end of the optimistic execution, you resolve the coherence, and this NDA function either commits its results to memory or it re-executes from the beginning. That's the idea. Okay, so let's go through this in a little bit more detail. So how do you actually resolve the conflicts? Basically, you keep track of the signatures of the memory locations that you've touched. This is a signature of the memory addresses that you read and written to. So you have a read signature and a write signature, and you compare it to the write signature of the CPU, essentially. And then you send the signatures, and the coherence actually gets resolved on the CPU side in this particular design. And the CPU says you should commit what you've done because we didn't conflict while we were doing this optimistic execution. Or the CPU says, please re-execute because here are potential addresses we conflicted in. And the CPU actually flushes those addresses from its cache at that point in time so that hopefully the re-execution completes without any conflict. Does that make sense? Okay. Then, of course, the question is, how do you identify whether you should commit or you should re-execute? Basically, you need to identify there is a violation, right? Let's take a look at that. So basically, here you need to really understand what are the necessary coherence requests. So coherence requests are only necessary if there's a conflict, meaning both NDA and CPU access a cache line, and at least one of them updates the cache line. So there are three possible interleavings of access to the same cache line. If the NDA reads and CPU writes, now this is bad because NDA didn't get the correct data, so this is really a coherence violation. If the NDA writes and CPU reads, actually this is not a violation, it turns out, and we will see that example, or you can read the paper in detail. If both of them write, they're also no violation because you can order these in different ways. Let's take a look at this one. The CPU writes over here, concurrent execution. CPU is executing, NDA is executing, CPU does a write to block Z, NDA does a read from block Z, and during this optimistic execution, there is no coherence check, but NDA reads the old value of Z, and this means that there is a coherence violation. CPU flushes Z to ZRAM, and NDA restarts from the beginning. No. Okay. But in this case, both of them are doing writes. Basically, NDA writes over here to Y, and then CPU reads from Y. There's actually coherence checks happen at the end of the NDA kernel. And there's no real violation over here because you can think of C4 and C5 to be ordered before this M5 over here. It's as if the CPU executed before the NDA. That's the idea over here. Okay, so you can go through the paper for more detail, basically. So for this to work, you need to provide architecture support clearly, and there's some overhead. This is not the simplest coherence mechanism, I believe. I think providing coherence mechanisms for these accelerators, especially in-memory accelerators, is a very important research problem going forward. Because if you want these things to be programmable, you really want coherence support. If you remember when we discussed in-memory processing, we discussed coherence as one of the system level issues that need to be handled for adoption or widespread adoption of this new technology, right? So for this, you need to solve coherence, and this is this paper solution. Basically, for coherence resolution, you need to keep track of the read set and the write set of the NDA kernel that's executed, and you need to keep track of the CPU's write set. Basically, these are the cache block addresses that you read during NDA execution, cache block addresses that you've written to, and cache block addresses that the CPU has written to during the same time. And at the end of the NDA kernel, you do the coherence resolution. So let's go through this relatively quickly. I guess I already said all of these. Oh. So there's more overhead that you need to keep track of. There's reasons for it. You can read the paper for more detail. So coherence is messy, basically. I think that's one of the takeaways. You need to basically consider every single possible corner case to make sure that you don't miss any updates in the end. Apparently my computer is missing something, so it's also old. Okay, we already discussed this. Basically, you use these read sets and write sets to keep track of which accesses happened during this optimistic execution. And the way this paper does it uses signatures to keep track of them. Clearly, you can use a linked list, again, which is not very efficient. But this paper uses Bloom filters. It uses counting Bloom filters. You can read the paper for detail. You've already seen Bloom filters. I'm not going to go through this in detail. So clearly, this helps easy coherence resolution because you compare two Bloom filters, right? And figure out if they match. Because you do the same updates. You do use the same hash functions in both places. Meaning that if you've updated the memory location or if you've touched the memory location over here, the same bits get set here as if the memory, so if you updated memory location A, or if you touched the memory location A, the bits that get set over here are the same as the bits that get set over here if you've written to that memory location, the same memory location. So that's why you can actually compare the Bloom filters. If there's any match in the Bloom filter, that indicates that potentially you violated something. Right? It may not be true because Bloom filter has false positives, as we've discussed, but you still need to ensure that that's not true or that is true. Okay, so basically it's easy to compare these Bloom filters, and it also allows for a large number of addresses to be stored within a fixed length register. We already discussed this. Bloom filters are a very scalable way of encoding sets. Right? A linked list is not a very scalable way of encoding sets, but this one's a very scalable way of encoding sets. As long as your false positive rates don't become unacceptable, this is good. Okay, and the paper has analysis of false positive rates. You can take a look at that if you're interested. Okay, so how do you do the coherence resolution? Basically, you essentially compare. And for every bit, basically. Any clean cache lines in the CPU that match an address in the NDA write set are invalidated, and NDA commits data updates. Okay. And if the conflict happens, the CPU flushes dirty cache lines that match the address in the NDA read set, and the near data accelerator invalidates all uncommitted cache lines, and it erases signatures and restarts execution. But the hope is that because CPU flushed all the dirty cache lines that match the addresses, the NDA will have them and will not conflict with them again. But there's no guarantee again. And this is always the problem with optimistic concurrency. Whenever you're optimistic about concurrency, meaning that you're assuming that you have some permissions, and you go ahead, and if you're wrong, you need to roll back. Once you roll back, you need to re-execute, and you could keep rolling back and re-executing. Because you may actually get to some other conflict, right? Again. Now, that's why people have developed a lot of fairness mechanisms for conflict resolution. One of the ways to ensure that you don't keep re-executing is maybe you tried several times and you re-execute it, and at some point you give up, you say, I don't want to get this conflict. At that point, you can say CPU stop, and the NDA goes and executes, and then you don't need to re-execute, right? Because there's no conflict anymore because you stopped one of the accelerators. Basically, the solution for conflict resolution, if you keep getting these rollback and re-executes in optimistic concurrency, is always stop one thread, for example. Okay, so let's go through the evaluation relatively quickly. This paper has extensive evaluation, which I'm not going to bore you with the details of methodology, but you can read it clearly. And a bunch of different applications, mainly graph processing applications with both small graphs and large graphs, and the hybrid transactional analytical database applications. And you can see the details in the paper. But basically, these are the takeaways over here. I guess, what is this? This is performance. Performance compared to CPU only. You don't do any offloading to NDA. And you can see that I think I've already shown you, I guess, CG and NG, coarse grain and non-cacheable. They're not very good. That's why they're not here. But there's also NDA only over here, near data accelerator. So one of the questions is always, why don't you execute everything in the in memory, right? And it turns out that's not always good, basically. Basically, you don't get as much performance because some of the code is much better fit to execute on the CPU. That's why you partition your program over here. Okay. So fine-grained coherence actually loses significant fraction of the ideal NDA's improvement, as we've seen. And okay, I think I already said that. And in the end, Conda gets close to the ideal NDA. But again, there's still a gap, as you can see over here, about 10% or so over there. So it's not the perfect coherence mechanism. And it does have overhead. I think complexity is one of the overheads. So how to simplify this sort of coherence mechanism is still an open problem, I think. Okay, but it's not bad in terms of performance. In terms of energy, it's also, I guess, not bad. It gets very close to the ideal NDA, as you can see, because it reduces the unnecessary coherence traffic. So ideal NDA means the same partitioning, the same offloading, coherence magically happens. So there is no rollback, there is no re-execution, and there is no coherence message, in fact. So it's magic. So you get relatively close to the magic, as you can see over there, in terms of energy. Okay, and there are a bunch of other results in the paper. These are actually more interesting results, I think, but the simulations take really long for some of these larger data sets. But you can see that the benefits of near data acceleration with the partitioning that Amirali has done is actually very high for larger data sets. If you're operating on much larger data sets, in-memory processing is actually even more interesting. You get 8x performance improvement over CPU-only execution, and I guess close to 8x performance over NDA-only execution. And there's some analysis of Conda compared to other coherence mechanisms, as you can see. This is one of the results over here. And there's a bunch of sensitivity analysis. Whenever you're writing a paper, it's always a good idea to do sensitivity analysis. What if you have multiple memory stacks and you distribute the computation across them? How long does it take to do the optimistic execution? Actually, if you have this sort of system, it makes sense to break the NDA kernels into smaller chunks to reduce the possibility of conflicts, right? That's the idea. If you have a very long NDA kernel or a function that needs to be executed on the memory side, the probability that it's going to conflict with the CPU increases with its length. So if I were programming something on this system, I would chunk my tasks. Or the system can automatically do that for you. In fact, there's some optimization that's not necessarily discussed in the paper, but it's discussed in a prior version somewhere. Basically, the system automatically chunks. It's possible also, right? The programmer doesn't need to do that. System says, okay, this is the end of NDA kernel. This is where I'm going to look at check for coherence. And you check for it. And if you check for it in a finer grain, maybe you didn't have conflicts. But if you went a little bit further and did the check after that point, maybe you'll get a conflict and you'll have to roll back all the way to the beginning. So the size of the function that you execute on the accelerator matters here. Effect of the signature size, of course, your signature size affects how much false positives you have, how much communication you need to do. Data sharing characteristics also clearly affects that as well. I mean, clearly there's hardware overhead over here that needs to be analyzed also, but you can see that also. Okay. I think I've already concluded. I've already said all of this, so I'm not going to talk about this. But I will, I guess, conclude with saying that there's more need for this sort of system support for near data accelerators, as we talked about it in the in-memory processing lectures. Coherence is a key problem. Virtual memory is another key problem. Runtime scheduling, partitioning of the data and partitioning of the code is a key problem. All of those are open problems. And I think coherence, this paper actually, as far as I know, it's the first paper that looks at the coherence problem between a near data accelerator and CPU. But I think there's more work to be done, because if you look at this paper, I think it's a good solution, but implementation-wise, it's not easy. It takes a lot of effort to implement this, I think. So if you can simplify this and get the benefits, maybe slightly lower benefits, but much simpler mechanism, that actually, I think, will become much more adoptable. Okay, if you're interested, you can now read that paper. Any questions? You have 3 minutes to ask questions, I think. Any ideas how to do better than this? Maybe not yet. Okay, I guess if there are no questions, we're done for today. I'll see you next week. Have a good weekend.